Cool, welcome everyone. This is the 2016 Major Emphasis Training on Hydraulics and Flow Tests. We'll just get right into it. If we can ask you to just not get on your phones for like 2 hours, it would be greatly appreciated. There's a lot of stuff here, and if you look down at your phone for a minute and look back up, you're gonna be lost, I guarantee you, because we're covering a lot of stuff pretty quickly. So, our objectives today, depth of knowledge is our main objective. We're really wanting to make sure everybody understands the why behind a lot of this. A lot of these are fairly complex topics, and it's important that we understand the why so that when we try to apply them, that they make sense universally as we do try to apply them. Frame of reference, kind of knowing the why behind things is really important with a lot of this. So we have a new DO manual, which everyone will get at the end of this class. And this class kind of outlines that DO manual, talks about, kind of follows that format. We have new pump charts, which you see hanging around the room. We're going to go over those extensively. Everyone should be pretty comfortable with those by the time we leave. We're going to talk quite a bit about nozzles, friction loss, target fire flow principles, new pumping operations, and then we really just want to get a baseline. Get the whole department on the same page with all this flow stuff, and this is a great launching point as we move forward. So this is a 2-hour class. We'll take a 10-minute break halfway through. And then there's 2 breakout sessions, one for captains and firefighters in the next room with Gino, and he's gonna go over, it's kind of a go or no-go decision-making model using your thermal imager, and then also talking about different water applications, smaller droplets of water on vent limited fires, which we'll talk a little bit about in here too. And then really stressing that depth of knowledge, really understanding the why. This class is really designed to give you a good baseline. This stuff is written in, frankly, exhaustive detail in the new TO manual, so there's a constant reference for everybody to go back to with all this stuff. So since why is important, let's start with why. So we conducted the massive scale flow test that we did a few years ago, or last year, or whatever it was. So why did we start flow testing? Flow testing is nothing new to PFA. We started this with Captain Albrecht and the Hose and Nozzle Committee when we got our new TFT nozzles. We did a lot of flow testing, and that's where we got our chuck charts. In fall of 2013, Captain Borello went to Nozzle Forward, brought those techniques here at PFA, brought the new hose load techniques, and started doing some small scale flow testing. We really recognized the need for more. He got moved to the ladder, and that's when Hal and I kind of started taking it over. In 2014, the DO Academy Hydraulics class, we kept finding anomalies, and people were asking really good questions. They were asking why? Why is this? Why is that? And we didn't have good answers. And so we wanted to flow test to provide good answers. We also started reading. We've got a whole binder full of articles here, plus many, many more. All the articles out there tell you that the only way to really know your flows is flow testing. We talked to industry experts, Jason Goodell out of Loveland, who's on the NFPA host committee, and Dennis Aguirre, who's one of the foremost authorities in the country right now on flows, flow rates, hose lines, nozzle selections. When you talk to those people, they also recommend flow testing. There's also been line of duty deaths where people, where firefighters have died in the line of duty, partially due to lack of fire flow. Fire flow referring to GPM versus BTU. They didn't have enough water to put the fire out for whatever reason, whether that was kinks in their line, poor hydraulic calculations, whatever it might have been. In cases where, they thought they were walking in the door with 150 GPM, and then for whatever reason found out they were only flowing 95, and that was a direct correlation to line of duty deaths. NFPA also recommends flow testing, and the bottom line is flow testing is the only way to truly know your flows. We just can't rely on traditional fire gun hydraulics for a lot of reasons, which we're going to cover in this class. So we needed a flow test, so we made a pitch to Chief Vandy. The idea was to flow test our equipment and get as much of our equipment tested as we could with multiple different engines, the hoses on those engines and the nozzles on those engines. We didn't want to just flow test a small section of hose and go from there. What we ended up testing was 7 engines, over 40 nozzles, over 5,600 feet of hose, so over a mile of hose. And we had over 30 people directly involved in the flow tests themselves. And that's just the flow testing part, let alone the people who helped us with the DO manual and all the other ancillary projects that were kind of designed around this. So we've had a lot of help, and we feel like we've vetted it as thoroughly as we could. So how we physically conducted the flow tests, we had an engine hooked up with a stick of 2.5 to a flow meter. The flow meter is on the intake of the engine. The reason it's on the intake is water in equals water out as long as your tank to pump is closed. And that way we could switch our line configurations off the back of the engine without having to move the flow meter every time. The flow meter was calibrated in every test, before, during, and after every test, to make sure that we had consistent flows. You end up using a smoothbore nozzle to calibrate your flow meter. We also got 2 brand new calibrated pressure gauges. They're inline pressure gauges, and we put one at the tailboard right on the discharge and one right at the nozzle. We did that for a few reasons. There's so many variables in flow testing that we really wanted to make sure that we were comparing apples to apples and eliminating as many variables as we could. So having a consistent discharge pressure gauge instead of trusting the engine pressure gauges was important for our accuracy. What we found with that was that our discharge pressure gauges were very accurate across the board. We didn't find any that were more than a couple pounds off. We also had a pressure gauge, like I said, at the nozzle. That's for 2 reasons. One, we got a very accurate nozzle pressure. With automatic nozzles, that can be an issue, so we'll talk more about that later. It also determines an accurate flow, and more importantly, it gives us a very accurate nozzle reaction. So if we know our pressure at the nozzle and our rate that we're flowing at, we can calculate a very accurate nozzle reaction. Lastly, we can subtract our nozzle pressure from our discharge pressure, and that gives us an extremely accurate friction loss count for those sections of hose. So that's kind of how we did the flow tests. That led to a lot of data. This is just a ton of data that we had to sift through. So we had to figure out a way to compile it and organize it in a manner that we could digest, so we accumulated all the charts. So what you're seeing here is the data culmination for line pressure on 1 3/4 pre-connects with TFT nozzles. We have 200 feet going across the top. We have 100-foot sections separated into standard pressure and low pressure going across at various different flow rates. What we ended up doing for the line pressures that you're going to see on the charts around you was taking we threw out the 2 high, threw out the 2 low, took an average, a mean, and a median for all the remaining numbers, and then that's where we got the numbers that you're going to see throughout this presentation and on the charts. We have these same numbers for nozzle pressure, so this one was total line pressure, this is nozzle pressure. We also have friction loss. Everything you've just seen is for 1 3/4, we've got the same numbers for 2.5, 3-inch, supply to Y, high rise, and a bunch of random anomaly flow tests. What we found is that we really have the right tools for the job. We've got good nozzles that are performing and doing what we need them to do very well and very efficiently. We can use our tools, and not just our nozzles, but our tools meaning our entire hose line package, our hose line deployment package. We can use it more effectively and efficiently at very little cost to us. Kind of liken this to, you can force a door with just an axe, but using an axe and a Halligan, you're obviously going to be a lot more efficient. So kind of looking at our hose deployment package in a very efficient manner in order to be fast and get the job done. So, we weren't sure when we started this if we were going to end up needing new nozzles. Once we started flow testing and found out that our nozzles were pretty good, NIST and UL is currently doing research on flows, flow rates, nozzles, smoothbore versus fog, flow rate, all that kind of stuff. So that data should come out here in the next year or so, and it's going to take another year or so for the fire service to kind of digest it and figure it out, and then another year or so for manufacturers of nozzles to come out and start improving nozzles or making changes or based on the results of that. So it didn't make sense for us to buy nozzles right now. They're expensive. They're like $1,300 a pop for the ones that we have. So it didn't make sense to do a wholesale change now when in 2 or 3 years and we've got much better data, we can make a different decision. But I mean, frankly, the nozzles we have are very good, especially when used in low pressure mode. So a lot of this has to do with fire behavior. When I first met with Jason Goodell out of Loveland and we started talking about flow testing and how to do it and what they did, we found that, he said that for every door you open, you're going to find 10 more closed doors behind it, and we definitely found that to be true. The rabbit holes run pretty deep on this topic. And it's no different with fire behavior. PFA had to look at the research, and we had to figure out how do we adopt this stuff, because there's a lot of factors that contribute to how a department deploys this package. We have to ask ourselves, how does it deploy to us? NIST and UL told us about petroleum-based fuel product, flow path, door control, just to name a few, and we have to ask the question, how does it apply to us? The same process kind of drove flow testing. There's a lot of data out there. All these articles and then some, like I was talking about. And you can open 2 articles in the same magazine, and one of them will tell you you're an idiot if you're not using smoothbore, and one of them will tell you you're an idiot if you're not using fog nozzles. And they talk about flow rates and all that kind of stuff. And I would encourage everyone to read more on this stuff because it's super interesting. Flow rate, hose line selection, GPM versus BTU, water droplet size. Just realize there is conflicting information out there, and people have staunch opinions, and they're valid. I mean, there's good, valid points on both sides of the argument. It's just a matter, when somebody tells you that this is definitely the way to go, they're probably not taking into consideration your department's deployment model. Because we have to look at how this all affects us. We're not Boston, New York, Oakland. We don't have 6-person engine companies. We can't throw 5 people on a hose line. We can throw 2, maybe 3 people on a hose line, and sometimes 1. So that affects our deployment options and how we deploy our hose lines, and we have to take that into consideration. We have to look at our deployment package, which includes staffing levels, how many people are arriving on scene and when they're getting there, what jobs we're trying to get done on the fire ground, building demographics, how much commercial versus residential we have, what kind of fires are we fighting. You know, we're lucky at PFA that we don't have a jurisdiction that's nothing but industrial or nothing but high-rise. We have a mixed variety of structures in all of our areas. So a common hose line deployment option on our engines can work for everybody. We have to look at our benchmarks. What jobs are we trying to get done and when are we trying to get them done? Our deployment model, which includes our standards of cover and our arrival times. Who's getting on scene and when are they getting the jobs done? What we found looking at all this is that some very simple and practical solutions can equal a more efficient deployment at very little cost to us. We've already got the equipment we need, we can just use it smarter. The cool thing is that when you start disseminating all this data and really digesting it, there's only so many ways you can deploy it. You only really have a couple nozzle options and a couple hose line options that'll really get the job done. So different departments will look at this data and their deployment packages end up being very similar because there's only so many ways you can skin this cat, and they might make a few different changes as far as like hose line selection and things like that, or I'm sorry, nozzle selection. But you find out the results are fairly similar. Loveland did flow testing a few years ago. They have a very similar deployment model as us. West Metro did a great nozzle study in 2005. I would encourage everyone to read that. That's a culmination of articles. There's really good information in that. And then the cool thing was when we gave this to the ops team, about a week before we sent it out, Hal sent me that PowerPoint that he found online from a department outside of Seattle. We've never met, we've never talked to. He found this PowerPoint online and it was slide for slide, almost exactly the presentation we gave to ops, like literally almost slide for slide. So it's just somewhat vindicating to see that there's only so many ways you can process this information.
These references that we researched are available on Target Solutions if you're interested.
Yeah, they're in the back, the last page of the DO manual, and they're stored at Target Solutions. So, how we got here meaning sitting in front of you, standing in front of you, teaching this today. We recognized the need for flow testing. We approached Chief Vandy and made a presentation to the operations team. They signed off on kind of the theory behind everything, which included new target fire flows, hose line standardization, new DO manual, and equipment changes. Then we had to figure out a way to get this to the department. So a lot of this had to do with fire behavior, so we presented it to the fire behavior committee, and they gave us this time slot for this presentation here. That's this major emphasis training. And for those that don't know, we're gonna have two eight-hour days now. We're gonna have one in the spring and one in the fall. We've got our second one coming up in November. So in November, we'll spend the whole last half of that day doing the hands-on that support this entire training. So getting into the meat of the class, some things to know before we start. First off, this is the tip of the iceberg. These topics go so deep and there's so many rabbit holes to chase. There's so much more information. We're really just kind of giving you the deployment model that we've chosen and the whys behind it. But this reading is really interesting and I would encourage everyone to get behind it and try it. So what we're ultimately after here is accurate flows, which means accurate pressures. And the way we get accurate pressures is accurate hydraulics. So we're kind of gonna follow hydraulics to teach this class. We're gonna talk about nozzle pressure, friction loss, appliance loss, elevation, and its relation to total line pressure. And we're gonna use that format to kind of drive that conversation. We're gonna talk about how important accuracy is, how much being just a few pounds off makes a huge difference. And we're gonna talk about nozzle reaction, nozzles, friction loss and mystery hose, flow rate and hose line selection. One of the things you're gonna hear us mention is an increase in target fire flow from 150 GPM to 180 GPM. We're gonna talk more about the specifics of that later, but I'll be mentioning it before we end up going over it in depth, so when you hear me say it, just know that that's coming. With flow rate and hose line standardization, we're gonna use the box idea and the standardized weapons idea to kind of simplify our hose deployment package. We're gonna go over our new pump charts and then go over some new pump operations. As far as questions go, if you have them, please ask them. Like I said, a lot of the stuff we can chase rabbits pretty quickly. So if it's kind of heading down that road, I might turf it for a break, or you can ask us later. But if you have questions, please do ask, but don't be offended if I turf it to answer later. So let's talk about nozzle reaction, because understanding nozzle reaction is pretty paramount to this whole conversation. So what is nozzle reaction? It's Newton's third law, right? For every action, there's an equal and opposite reaction. So nozzle reaction is the relationship between GPM and PSI as it leaves the nozzle. So water's got a lot of mass, right? It's almost 8.5 pounds a gallon. So as it leaves the nozzle, that mass leaving the nozzle, I feel the effect of that. I have the opposite reaction of that, right? If I increase the mass or the water, or I increase the nozzle the nozzle pressure, the velocity, either one of those make the nozzle reaction go up. So if I've got a high nozzle pressure and a high GPM, I'm going to have a high nozzle reaction. Does that make sense? If I want a high flow rate and a low nozzle reaction, what can I decrease?
Pressure.
The pressure, right? My nozzle pressure. So there's a lot of studies out there that talk about what can firefighters handle on the nozzle. And it's not, I'm a badass, I can handle whatever you can give me. It's what can you truly be effective with. So if I'm fighting nozzle reaction, I'm not paying attention to impending signs of flashover, to radio traffic, where I am in the building. So you want a manageable nozzle reaction that you can handle, right? And that you can handle while doing other things. So there's a lot of studies out there that talk about this. The numbers float around a little bit, but these are the numbers we're using at PFA. Multiple studies show that the maximum nozzle reaction a firefighter can handle, one firefighter is 70 pounds, two firefighters is 80 pounds, and three firefighters is 90 pounds. These are also on your handouts. They're on the top, that colored chart, because I'll be referencing them quite a bit. Once you get above about 100 pounds of nozzle reaction, you've kind of reached a law of diminishing returns, and you're no longer really truly a hand line. You're now into a master stream or a monitor, and you're using the design features of those tools to help manage that nozzle reaction. So that's why those don't go a whole lot more over 90 or 100. Basically though, above that, for every 10 pounds of nozzle reaction that you encounter, you need to add another firefighter to help mitigate that. What they find that this leads to is firefighters gating back, because when you gate back, what are you decreasing? GPM, right? When you gate back. So if your GPM goes down, your nozzle reaction goes down, exactly. So that's kind of the fallback in your head. If you're fighting nozzle reaction, you start gating back. Well, if you're gating back, you're also taking the bullets out of your gun. You don't have the GPM needed to fight the BTU that you're encountering. So it can be a dangerous practice in an ideal H on a fire. So that's nozzle reaction. We're gonna move on to nozzles. We have two nozzles on our engine. We've got smooth bores and automatic fogs. So we're gonna kind of compare and contrast the two. I know there's a lot of debate in the fire service over smoothbore versus fog, and we're not here to settle that debate in any way. But what we can tell you is some of the reasons we use automatic fogs and why they're advantageous to our deployment model. So smoothbore nozzles have the designed nozzle pressure of 40 to 60, with 50 being optimal for a hand line, and 70 to 90 for a master stream, with 80 being optimal. But these are becoming debatable, which Hal will talk about.
Also, NFPA specifically says that it's supposed to be operated at 50 PSI. However, you have situations like on our 1-inch tip for our high rise where you don't have a significant amount of back pressure. So a 1-inch tip will give you 210 gallons per minute. 15/16 will normally give you 185 gallons per minute. But if you pump a 15/16 hot, then you can possibly get upwards of 200 GPM out of it while creating additional back pressure so that you have less kinking.
So a lot of the things Hal and I found with these flow testing stuff was that these tried and true numbers and these hard numbers and some of the hard concepts that you kind of get used to as you go through like ISTA hydraulics can be massaged a little bit, and you can make them work better for your application. So flow rates, the difference between a hand line and a master stream. The breakover point, if you read an ISTA text, is 350 GPM. A lot of people say that's closer to 300. I think it's actually less, about 1 1/8 inch tip on about 266 GPM. The reason is, that's a lot of mass leaving the nozzle. We talked about nozzle reaction being the relationship between GPM and PSI, right? 300 to 350 GPM is an extra 50 GPM, which may not seem like that much, but that's a lot of mass. When you look at 50 times 8.5 pounds a gallon, that's a lot more mass leaving the nozzle, and it has a massive increase on nozzle reaction, which we'll look at later. So as far as flow rates on smoothbore tips, the cool thing about smoothbore tips is the nozzle diameter and the pressure at that diameter dictate the flow. There's only so much water you can force through a certain diameter nozzle. So what you're going to see here, these are the smoothbore nozzle flow rates that are on our current charts This chart is right up here, just like it was on our last charts. And what you're gonna see here is exact flow rates. So before we used to use the rule of thumb, right, which was like 200, 250, 300, 350, then we transitioned to master stream, 400, 500, 600, right? So what you're gonna find here is exact numbers, which we debated quite a bit. We understand the frustrations behind that, but we have some good reasons for doing this. So 1 inch is 210, not 200. Inch and an eighth is 266, not 250. An inch and a quarter is 328, not 300.
So we're interested in creating more frame of reference and for people to have a more thorough understanding, especially if you're trying to troubleshoot something. A couple of examples during our flow testing, we would use these solid bore tips specifically for calibrating the flow meter. Spaz was trying to get the PSI right for the amount of flow that he should have, and he couldn't figure out why the PSI was low, so it should be at 50 PSI. The reason was because he was going by rule of thumb, an inch and an eighth tip being 250 gallons per minute, but it's actually 266 gallons a minute. So that's one example. We also had an assignment not long ago with Target Solutions where we had a pull of 2.5. Some of the guys were noticing, and we'll kind of talk about this a little bit later with mystery hose, but mystery hose is larger than diameter hose, so it has a lower friction loss coefficient, which means it has a higher flow. So the guys were noticing that when they took it out to flow it, it had a significant amount of nozzle reaction. So the driver operator actually had a really good idea. He's like, we'll just go off the flow meter for what it's supposed to be because I think we're running this too hot. Well, unfortunately, he went by, again, the rule of thumb, which was 250, not 266. So we went from being wrong to being wrong. Then if you take our high-rise hose, for example, the 1 inch tip at 150 GPM is what is on our current charts. In order to get 150 GPM out of a 1 inch tip that should be 210 GPM, you'd have to operate it at 35 PSI. So can you imagine what a hose line is going to be like if you're operating it at 35 PSI? So we're trying to get away from this so that people are able to troubleshoot things and figure things out accurately.
So this goes back to that depth of knowledge, right? We're driving home the point this entire class of how important accuracy is. So we have to start with accurate numbers because there's any amount of variables on a fire ground that can affect our accuracy. We can have a gauge that's bouncing all over. There's lots of things that can happen. So we have to start with the most accurate numbers that we can, because if we make a 5-pound error on every from the nozzle to the friction loss all the way down the line, we end up being 10 or 15 pounds off, which makes a huge difference. So, beat that horse. The advantages of smoothbore nozzles is that they pass debris, they're extremely tough, and they're almost maintenance free. It's a ball valve with a pipe sticking on the end of it. It doesn't get any more simple than that. They're not gonna break, there's nothing even to go wrong with them. Disadvantages is a lower back pressure. So as you force water through a certain diameter, as you decrease the diameter, you increase what's called back pressure. So if you can imagine, if you've got a garden hose, and I stick my thumb over the garden hose, I decrease that diameter of the tip, thus increasing the back pressure, the pressure that stays in the hose line. So one of the golden rules with smoothbore nozzles is you don't want to go larger than half the diameter of the hose. So if you've got a 2-inch hose, you don't want larger than a 1-inch tip. And that's so that you don't lose back pressure, because the fact of the matter is smoothbore nozzles kink easier than automatic nozzles. It's just a fact. That's not like, it's not, you know, in that debate between smoothbore and fog nozzles, like that's just fact. Smoothbore nozzles just kink more. And all that means is that you have to manage those kinks, right? It's a disadvantage, but it doesn't mean it's completely not manageable. So all you have to do is put more people on those lines to manage the kinks. So to manage that lower back pressure and the higher increase of kinks, more people need to staff the line. So we need to get in the habit here of when we put a 2.5 into service, which is where our smoothbore play, or our high rise, that's a 2-crew line. We need 2 crews on that line. I know there crews are out there that can move a 2.5-inch hose effectively as a 2-person crew, but not everyone can do that. So we need to, once again, think about our hose line deployment practically.
There is a significant increase in nozzle reaction and weight of water in the hose line and everything. We'll talk about that too.
Right. Another disadvantage with, well, it's either an advantage or a disadvantage depending on how you look at it with smoothbore nozzles. Any decrease in pressure, so a kink in the line, a miscalculated pump problem, equals decreased nozzle pressure, because you're under pumping it, and if you decrease the nozzle pressure, your stream quality goes away, right? So you're not going to be able to get the water where you want it. Some people see that as an advantage. If I'm gonna fire and my stream quality goes away, I know that something's happened and that's my cue to retreat. Some people see that as a disadvantage, because if that happens, you can no longer get the water where you want it as you're retreating and you're putting yourself in increased danger. Both of those have valid points.
While we were flow testing with the 1-inch tip, we noticed that a curve, a very oblique curve, about 8 to 10 feet behind the nozzle, had a significant effect on the hose stream. And then you straighten that hose out and your stream improved. So it's amazing how easily it's affected.
It really is. An advantage of an automatic nozzle is that across a flow range and at varying nozzle pressures, you have a good looking hose stream, right? It's designed to give you a good looking hose stream. The disadvantage there is you might not know because the stream quality looks good when your flow has decreased, but we'll talk about how we can manage that later. What has everyone heard about smoothbore nozzles? What's the big advantage? You guys know it, just say it. Reach and penetration, right? Not true. So we did our own reach test. Want to pause it there, Hal?
Yeah.
So we've got, they've hooked up 2 nozzles to a Blitzfire. These are the same flow rates we're using. They have a 15/16 tip and a fog nozzle. Both of these are flowing 180 GPM, which is our new target.
185.
185 GPM.
At the same exact PSI.
Which is our new target fire flow. So we're gonna look at these streams side by side. We have the fog on the right and the smoothbore on the left.
And they peed on them.
So they pee to them just to prove that they're at the pressure. I think you went too far, Hal. I think it's closer back here, a little further.
Where are you looking for?
A little further back. Yeah, right there. So you can see the streams here. This Hal backs up just a little bit. With the fog nozzle on the right and the smoothbore on the left. And you can see we've actually got a tighter grouping on our fog nozzle than we do our smoothbore. And at this angle, it looks like the smoothbore is going a little bit further, but we'll see another angle here in a minute that shows that they're pretty much equal. So then they switch out tips on the Blitzfires and they increase their flow to 500 GPM. So we see the same thing. We've got a smoothbore on the left and a fog on the right, and we see our effective streams. Well, I mean, once again, you can see they're almost equal. In our reach test, we found that our fog nozzles actually outperformed it. Here's a look at the stream quality side by side. And here we can see right there towards the end, you can see how equal those were. Back that up again a little bit, Hal. Yeah, from right there. Yeah, here we go. So here at this angle, we can see, they really are about the same. So I don't know why that's still written in textbooks or why that's such a popular thing. Reach has everything to do with droplet size, GPM, and velocity at the nozzle, and velocity equals nozzle pressure.
Mass and velocity.
So we did our own reach test. This consisted of me running around in a rain suit while we were flowing nozzles off the engine and marking them with cones.
And they were set at 32 degrees, which is supposed to be optimal.
Right, we had a little protractor out there, we were measuring it. And what we found is that our fog nozzles outperformed our smoothbore in every situation. So here we have the Blitzfire with the automatic fog, an 1 3/8 tip and an 1.5 inch tip. And you can see that the automatic fog did a much better job as far as reach goes. This is also showing the high and the low of the stream. So the max throw and the least throw. Our 2.5 inch fog outperformed all of our 2.5 inch tips, even when they had a stream straightener, which we'll look at a little bit later. The effect was a little less drastic. We had about a 15-foot increase versus like a 25-foot increase here. Also with our 1-inch high-rise tip versus our 1 3/4 inch standard and low pressure, we outperformed that with our fog nozzle as well. We also found a tighter grouping in low pressure and a very similar reach distance, which we'll further examine later, between standard and low pressure on our 1 3/4 nozzles. So stream straighteners do help. Here, stream straighteners take that turbulent flow, make it laminar, thus increasing your laminar flow at the nozzle, which increases your distance. So here's an 1 1/8 tip with no stream straightener, an 1 1/8 tip with a stream straightener, and we see that we get about a 13-foot increase and a slightly tighter grouping. So automatic nozzles are the other nozzles we have on our engine. They provide a constant nozzle pressure across a designed flow range. So what that means is they have a flow range and the nozzle pressure remains constant. So on a smoothbore nozzle, if you increase pressure, you increase if you increase line pressure, that pressure goes to the nozzle, thus increasing your nozzle pressure, thus increasing your flow. With an automatic nozzle, there's a spring inside that regulates that flow, that allows for a somewhat constant nozzle pressure. We have these on our Blitzfires, our deck guns, and our 2.5 inch fog. And then of course our TFT and mid-force dual pressure nozzles, which are on our 1 3/4 pre-connects. These have a designed flow range of 70 to 220 GPM, so that's the low and the high, and they're designed to give you that nice looking stream across this flow range. So between 70 and 220 GPM, you're gonna have a good looking stream. We have 2 pressure settings, 55 and 100 PSI. One thing to note about these is that these nozzles are not completely interchangeable with our high-rise nozzles when you put the ball valve in the front in order to give them the breakaway feature. So that ball valve in the front basically acts as a reducer, and per our flow test, we had to account for an extra 10 pounds of friction loss, or I'm sorry, 10 pounds of nozzle pressure at the same flow.
Acts as an appliance,
It acts as an appliance, what did I say?
reducer.
Reducer, yeah, it acts as an appliance. So here's how automatic nozzles work. So there's a spring inside that regulates the pressure. So water flows in around the slide valve, it hits this front of this baffle, which when we blow it up looks like this. So there's a spring here, water hits this baffle, compresses this spring, and as more and more water hits that baffle, as we increase GPM, that spring helps regulate our nozzle pressure
As
and
we
make,
increase pressure,
what did I say?
increase GPM.
Okay.
You get increased GPM.
Right. So we'll show what this looks like. So as we increase flow, we basically widen the gap between the baffle and the stream straightener. So as we see our flow increase from 1 to 2 to 300 GPM, we see the gap between the baffle and the stream straightener increase, thus increasing the orifice, thus increasing our GPM. The spring is regulating the pressure, keeping a relatively constant nozzle pressure of 100 across the designed flow range. So that's what an automatic nozzle is doing for us. That's all relative though, right? So we have a designed flow range of 70 to 220 GPM. When I'm in standard pressure, what's the nozzle pressure for a fog nozzle? When you read a book. Someone say it, you're right. 100 pounds, right? So 100 pounds is relative. So at a low flow rate on an automatic nozzle at 70 GPM, our nozzle pressure is 90. And this is the chart that TFT uses in their manual, and we've done our own tests as well. If we increase our flow to 180 GPM, the nozzle pressure is actually about 110 almost. In low pressure, it does the same thing, it just varies a little bit differently. So one thing to note between standard and low pressure, once again, you have a max designed flow range for that nozzle, right? As you hit that max designed flow range, it doesn't matter whether you're in standard or low pressure, you've maxed out that spring, and eventually your nozzle pressures marry and then take off together. So at a certain point beyond the designed flow range of that nozzle, the nozzle pressure will increase exponentially and they'll go up together. So it's important to use the numbers on our charts. So here's our 1 3/4 pre-connect chart. We'll go over this in more depth later. We've got 2 flow rates. We've got 125 GPM for a car fire or dumpster fire, and 180 GPM for a structure line. And we've got the associated nozzle pressure. So at one flow, our nozzle pressure is 45, and at another flow, our nozzle pressure is 60. So that's why it's important we use the numbers that are on the charts and don't just blindly throw 100 PSI or 55 PSI at the nozzle, because we could be wrong. Here's a video that's going to illustrate what an automatic nozzle is doing for us. So what they have is they have a pressure gauge at the nozzle, and they've got a flow meter, and we'll see the flow increase and our nozzle pressure stay relatively the same. So here's the lower design flow of our nozzle, 70 GPM. We're going to look at our nozzle pressure. This is in standard pressure. We're at 90 PSI. Exactly what the chart told us. We're going to increase our flow. So now we're at 100 GPM. Our nozzle pressure goes up to about 100, which is what it's trying to relatively remain constant. Increase our pressure, our flow to 140, and we're still at that 104 maybe. Increase our flow some more. 170, still at that same 104, 105. So that's what an automatic nozzle is doing for us. If you did this same test on a smoothbore nozzle, you'd see that nozzle pressure just increase and increase and increase as your flow increases. And here we've seen at our max flow, our nozzle pressure actually came down a little bit, just like our chart showed us. So if we look at our chart, we saw that it comes up and it actually dips down a bit before it goes back up. So we have extensive data with multiple nozzles of what our nozzle pressures are at various flows. We've determined what our flows are. The point is, use the numbers off the charts like we talked about. So other things happen when you switch from standard to low pressure. So let's talk about that. How the nozzle is physically doing this is the first thing we're going to talk about. So in low pressure, you got a 55-pound nozzle, and in standard pressure, you have a 100-pound nozzle. I've always wondered why, when you turn that, you're removing 45 pounds of nozzle pressure. Why is that not harder to turn, right? It's just a little quick click. The nozzle uses what's called hydraulic assist. So basically, that spring we looked at earlier is inside of this mechanism, okay? And this is the baffle that the water contacts. The way these nozzles switch from low to standard pressure, water comes past this baffle, it goes into this hole, and in low pressure, it comes right out of these holes and into the stream. So it goes right through this device and moves right through the automatic control. In standard pressure, you end up plugging those holes, and that water remains inside of this automatic spring device, and that water pressure increases that spring tension from 55 to 100 pounds, and that's what makes it a 100-pound nozzle. Does that make sense? So when these break, they break to low pressure, because if they malfunction, there's a 55-pound spring in there, so they break to low pressure, which is nice because that's what we're going to advocate using. So other things are affected when you switch to standard and low pressure. The most notable of which is nozzle reaction. So here's various flows in low pressure and standard pressure, and then the associated nozzle reaction. So at 180 GPM, which is our target fire flow, in low pressure we have a 55-pound nozzle. Our nozzle reaction is 67, which is right under that 70 that we want to maintain, right? That exact same flow in standard pressure, we've got 100 pounds at the nozzle, and our nozzle reaction is 90, which is a 3 firefighter line. So just by making that simple switch and taking 45 pounds away at the nozzle, we've gone from a 3 firefighter line to a 1 firefighter line, which is substantial, right?
That's also really close to what an 1 1/8" tip is on a 2.5. That's 99 pounds.
Correct.
So, and you lose, what, 7 feet of reach?
Right. So that almost seems too good to be true, right? Because you have a much lower nozzle reaction for the same flow. So there's other flow properties that are affected when you switch from standard to low pressure, and we're going to talk about a few of those. What we wanted to do, we were making the argument that we should switch to low pressure as a department, and so we wanted to thoroughly vet that and really look at that critically, yeah, and say why not? Why should we not do it? So we started doing research. The first thing that's affected when you switch from standard to low pressure is droplet size. So one of the articles we relied on pretty heavily here was this one, Quantitative Approach to Selecting Nozzle Flow Rate and Stream. There's 2 parts of this. It goes into exhaustive, nauseating detail on a droplet's size and its ability to penetrate the hot environment, hit the hot ceiling, fall back through the hot environment, and land on the fuel and extinguish the fuel. What you find is that a larger droplet of water fares better in that path that the water takes, and a smaller droplet of water completely evaporates.
So the big difference here is surface cooling versus gas cooling. If we're trying to surface cool, you're better off with that bigger drop of water. If you're trying to atmospheric cool or gas cool, you're better off with 2 microns or smaller drop of water, which you actually get out of a standard pressure setting or higher pressure. That's more effective if you're trying to, say, prevent flashover by gas cooling. The larger water droplet is going to benefit us in our larger GPM model.
So Gino in his class is going to talk a little bit more about the smaller droplet of water and what that can do for us. And what's important to note is that it's not an either or, is that they're both tools to use in different situations, and it's important to understand those different situations. So when you talk about gas cooling, you're putting a very small water droplet, almost a mist, in to cool the gas, versus a larger droplet, which is your surface cooling, which is like surface cooling the surfaces in this room to cool them down and prevent them from off-gassing and creating more flammable gas, and also surface cooling the fuel that's burning itself. So both of those end up making a difference, and they both have applications, and it's not right or wrong, or either or, it's just a different application in both models.
The European model is looking at more the high pressure, smaller water droplet. They use things like fog nails, so if you Google that kind of stuff, it'll talk about the gas cooling.
It's really interesting. There's a lot of good research done on that.
It's definitely not a 2 camps either or kind of thing. It's the right tool for the right job.
Right. So that whole diatribe is basically to say, in a high GPM flow model, which we employ in most of our fires, a larger droplet of water does not have a negative effect on our ability to A, cool the atmosphere, and B, cool surface cooling. Does that make sense? There's a lot more. You talk about the tip of the iceberg, you can spend days and days reading about this. So the other thing that's affected is velocity and reach, right? We're taking 45 pounds away from our nozzle pressure, so we can expect our reach to be diminished. Well, let's look at that. At the same flow, we had a max reach and standard pressure of 142 feet, and in low pressure, we had 135 feet. So that's a 7-foot difference across 140 feet, which is a 5% decrease in reach for 26% decrease in nozzle reaction. Increase in nozzle reaction.
Right.
So it doesn't make a whole lot of sense when you look at reach to not use low pressure.
Especially because that's over 142 feet. We're not talking about something that's 50 feet away and we're losing 7 feet.
Right.
And then also tighter grouping and larger water droplets.
Right. Like you said, we see a tighter grouping here. We're getting more water where we want it. So what it comes down to is nozzle reaction, which has a direct effect on our staffing. So if I'm first unit of fire today and I'm the firefighter, I'll pull the hose line. My captain will help me with the hose line. My DO is pumping, but the help I get from my captain is going to be sporadic. He might be checking the thermal imager. They might be checking flashover conditions. They're paying attention to radio traffic. They're going back to get more hose. The point is, there's a lot of times when I'm going to be on the nozzle by myself. So I need a manageable nozzle reaction for one firefighter. And nobody's doing anything wrong. It's not like the captains are not backing us up on purpose. It's just we have to really look at our deployment model realistically and say this is the situation we're in and we have to account for that. So we can have a high flow rate of 180 GPM with a low nozzle pressure, nozzle reaction of 67 pounds.
And bear in mind, that's still a 2 firefighter line. But if you go too high, then one firefighter can't handle it.
Right. PFA also needs a standard. I know it's almost funny, like when you go to the pump pit and your captain's like, oh, put a 1 3/4 line in service. Well, what flow? Am I in standard or am I in low pressure, right? It's almost like a joke, but it's really not that funny when you're on a fire. So let's say I'm on engine 10 and we're a low pressure engine company, and engine 3 comes up and pulls a line off of their rig and they hook it up and they're in standard pressure. Well, if I pump them at a low pressure setting and they're in standard pressure, I'm going to under pump their line and take the bullets out of their gun. They're no longer going to have the flow they need to combat the fire that they're facing. If the opposite is true and I'm a standard pressure engine, engine 3 pulls up their low pressure engine, their low pressure line, I'm going to over pump them, thus increasing their nozzle reaction, which could put them in a dangerous spot with nozzle reaction. So it's important that we have a standard. The point with all of this is, if we've thought really critically about switching from standard to low pressure as a department, and there just really aren't the negative consequences, of which there really aren't many or really any,
7 feet of reach.
don't override the benefits we get from switching to low pressure. So that's the new standard in PFA. Another benefit of these TFT nozzles is a slide valve versus a ball valve. So slide valves, I have a breakaway nozzle, a cutaway if anyone wants to see this. It just allows the water to remain more laminar as it moves through the nozzle, which gives us the ability to gate back. Is gating back a bad thing? Anyone have thoughts on that? When is gating back a good thing?
Move the line.
Moving the line might be, or if we're on a car fire or a dumpster fire, which is something we regularly use these lines to fight, right? So if I'm at a dumpster fire, which I'm not trying to combat flashover, and I got the nozzle way above my head, I can gate back a little bit, reduce my flow, and if I'm still being effective, that's fine. If I'm in a structure fire and I gate back, I'm decreasing my flow, I am potentially taking the bullets out of my gun, and I can no longer combat the BTUs that I'm facing. So gating back in a structure fire is not a good thing. So every nozzle has its strengths and weaknesses. So we've talked a lot about both these nozzles. Let's compare and contrast them a little bit. Smoothbore nozzles are very tough and very simple. They got us there over automatics. Automatic nozzles require maintenance, but we're going to talk about managing that here in a second. Smoothbore nozzles have a known flow and a known PSI, but that means that a loss of pressure equals a loss of stream quality. We kind of talked about that already. That could be an advantage or a disadvantage depending on how you look at it. With an automatic nozzle, you'll read articles that flat out say automatic nozzles have no business within a structure fire. One of their arguments behind that is a decrease in flow means that you still have an effective stream and that you don't know if you have a loss of pressure, thus decreasing your loss of flow, or thus decreasing your flow. So really training is what makes up for that. We can overcome that if we build really good muscle memory of what 180 GPM feels like in low pressure on these nozzles. So you can feel a pretty drastic difference of even 10 pounds of nozzle reaction. So get used to how that feels when you're standing, kneeling, pinching it on your hip, sitting on it with a clamp. Get used to what that 180 GPM and 67 pounds of nozzle reaction feels like, because when that nozzle reaction decreases, that's your cue that you've had some sort of loss of pressure. So once again, we can overcome that disadvantage with good training. Smoothbore nozzles, they kink more. They just do. I'm sorry, the hose lines kink more, not the nozzles themselves. Once again, it can be managed, 2 crews per hand line on a 2.5. Automatic nozzles have increased back pressure because the orifice size is smaller and that spring helps hold that back pressure inside the hose line. And they don't kink as much, which is a huge benefit to us. We have a deployment model where we only might have 1, maybe 2 people on a hose line. So this is a tool we can use to make our job easier in that sense. We talked a little bit, briefly talked about nozzle maintenance. Let's talk about how we're gonna mitigate that. We're gonna be sending back all of our nozzles to TFT to get serviced. What that's gonna mean is no more field servicing. So field servicing, if you're not doing that now, is basically cleaning and lubricating the nozzle basically at the station. It's pretty easy to do. The reason we're getting away from that is if once you start field servicing, you have to continue doing it. So when we send our nozzles back to TFT to get like professionally serviced, they take the nozzle completely apart and they put a really thick, almost like axle grease on the parts that need, on the gaskets, basically that need lubrication. So when we field service, we use like an oil that we pour down into the nozzle to get where we need it to get. So that grease that TFT puts in is very resistant to both flow and both water flow and foam. So when they say that if you keep your nozzle clean, it should pretty much work indefinitely for 5 to 7, maybe even 10 years if you keep your nozzle clean. The problem with the oil that you put in there is because it's thin and because it has to get into where it needs to go, the water and foam also removes it quickly. So once you start field servicing, you have to continue field servicing regularly. So if we keep our nozzles clean, we shouldn't have to field service if we get them serviced. So we're getting nozzle covers. This is the first prototype. We got a couple more. Hopefully one will be done today. And basically they're just covers that'll sit while they're on the engine. And if we can keep 80% of the road grime off of these nozzles, that is a huge benefit. So that's something we'll be moving to in the future. We're also going to do annual hose and nozzle flow tests. It's important that we flow test our hose to make sure our friction loss isn't getting away from us, and our nozzles to make sure they're performing adequately. So we won't do any more field services. We'll do the annual nozzle tests, and then if they're showing deficiencies, we'll send them back at that time. So we just spent a lot of time talking about nozzles, nozzle pressure, nozzle reaction, all that stuff. Continuing down the line of total line pressure, we're next going to talk about friction loss. So friction loss, as water moves through a hose, energy is lost due to friction as the flowing water contacts the liner of the hose. This is the difference between laminar and turbulent flow. So as water flows through a hose line, it makes contact with the edges of the hose and it makes turbulent flow along the edges, and we get a nice laminar flow through the middle. If we increase the velocity of our water, thus increasing our GPM, we'll eventually reach the point of what's called critical flow. This is where the water becomes so turbulent in the hose line, there's no laminar flow left. So let's say that for 1 3/4 our critical flow is 220, and I'm kind of making that number up, but not really. Anyway, if I keep increasing my pressure, I'm not going to increase my flow because I'm at critical flow. The water is so turbulent in that hose line. In order to realize more flow, I need to increase my diameter, which is why at a certain flow, you step your hose line up, which is why we have 2.5, because we're not at critical flow at those higher flow rates. There's a couple videos we'll watch to show us this.
If you look at this dye as it goes through this water, you'll notice it's cone shaped, and that's because your friction loss occurs during or around the wall of the pipe, and then the water that's immediately adjacent moves a little bit faster, immediately adjacent moves a little bit faster, the water in the center moving the fastest.
So there's our nice example of laminar flow. The next video we'll watch shows us critical flow. So it's basically the same thing. We're injecting dye into a water stream, and we'll see as the pressure increases, we'll see our flow, we'll see our turbulence increase up to the point of critical flow here. And you'll see critical flow when it happens. It's pretty obvious. There it is. So at that point, increasing pressure will no longer increase GPM. We've reached critical flow for that hose line. So that brings us to mystery hose. So we kept finding anomalies when we were flow testing. We were getting friction loss results, obviously, but none of them were, none of the mathematical methods out there, the accepted mathematical methods, were matching the friction loss that we were getting on our hose, and we couldn't figure out why. And it wasn't until we started reading an article that we found out that hose is basically not true to advertised diameter. So 1 3/4 hose is not 1 3/4 hose. Our 1 3/4 hose is closer to 1 7/8. Our 2.5 is closer to 2 3/4, and our 3 inch is closer to 2 1/4. This isn't a PFA problem, this is a National Fire Service problem. So there's a lot of different friction loss formulas that we can use. There's the official formula, and then there's rules of thumb. We don't use the friction loss formula on the fire ground because it's pretty hard to square things on the fire ground and then do a lot of math, right? So we have these rules of thumb that give us things that are numbers that are pretty close to the official formula. So there's the hand 12, the hand 9, the Q squared, and the drop 10. We used the drop 10 for quite a while at PFA. It was super simple, it was easy and quick. It worked on different diameter hoses. The problem is these work on true to diameter hose. So if you have 1 3/4 hose, this will work all day. But if I have 1 7/8 hose, it doesn't, the math for that, I'm sorry, I can do 1 3/4 math all day long, but if I don't have 1 3/4 hose, the friction loss isn't gonna be accurate. Like I said, this is
Just to give you an idea
Oh, yeah.
of what Spaz is talking about, what do you pump right now for your common attack line?
low pressure 200
Low
foot.
pressure, what do you typically pump at? 150 GPM at what?
Someone say it,
150
somebody
PSI,
knows it.
Right?
150.
150 PSI actually gives you closer to 200 GPM. So because of that larger hose, it's a lower friction loss coefficient, and you have a larger flow, which means you have 87 pounds of nozzle reaction.
So it increases our flows. So NFPA did a study, and here we see this is all 1 3/4 hose, this is all 2.5 inch hose. So what they did was they sent all these different brands and models of hose out to like 7 or 8 different fire departments who all did independent flow tests and diameter tests. And what they found is that all of this hose that's advertised 1 3/4, what they found at test pressure, which was pretty low in most cases, which is between 10 and 50 PSI in these tests, here's the actual diameter, 1.96, 1.98, 2.01. So that's 1 3/4 hose, that's almost 2 inch hose. The same is true with our 2.5. This is all advertised 2.5, and we see our actual diameter, 1.28, 1.83, 1.81, 1.72.
You mean 2?
2.
You're saying
I'm
one.
saying 1. Yeah, you're right. So yeah. So our 2.5 is actually larger than advertised diameter 2. The other problem is the hose also creeps over time. So as we continue to use our hose, our diameter increases just from use. So it's important to flow test continuously and over the years so that we realize we have accurate friction loss. What does NFPA say about this? NFPA 1961, which governs fire hose, this is the entire chapter. This is 100% of what this standard says about hose diameter. The hose shall have an internal diameter not less than the trade size of the hose. So that means we can't go any smaller, but we can kind of go infinitely bigger. So I could technically sell 1 3/4 hose that measures 5 inch diameter. So there's a lot of people kind of advocating for this, for a change in truer diameter hose, but it's going to be a long time before we see the downstream effects of this. So it's not a huge problem as long as we conduct flow tests and know our friction loss. A small increase in diameter makes a big difference, which brings us to the third principle of friction loss. For the same discharge, friction loss varies inversely as the 5th power of the diameter of the hose. What the hell does that mean? Basically what that means is you increase diameter, your friction loss decreases. It further says the larger your hose is, the bigger this anomaly takes place. This is proved when we look at our drop 10 method comparing 2.5 to 3 inch hose. Once again, if we use the drop 10 on true to diameter hose, it gives us accurate results. So let's use that to explain this theory. So if I'm doing math on 2.5, my drop 10, I have 300 GPM on 2.5, 300 GPM on 2.5. I take away the last number, I take 10 away, and I get 20 PSI per 100 feet, right? What's my next step if I'm on 3 inch? Cut it in half, right? Divided by 2. What did we just prove? A 1/2 inch increase in diameter has half the friction loss. Does that make sense? So that drop 10 method perfectly illustrates how much a small diameter increase in hose has an effect on friction loss. The problem is obviously greater the larger the hose diameter. It also has something to do with hose weight.
So on your 1 3/4, if it's actually an 7/8 inches, you're carrying an additional 17 pounds of water that you cannot do anything with. It's not helping you in any way. And then if you look at like 2 inch to 2.5 inch, it's 47 pounds more per 100 feet. So here's the interesting thing is we may actually be looking at 2 inch for our large hose line. The reason being is if you put an 1 1/8 tip on a 2 inch hose line, you're still getting 266 gallons per minute. Would you rather take that 266 gallons per minute to the fire with 47 pounds less per 100 feet that you're dragging behind you? So,
Yeah, it makes a difference. So let's look at mystery hose and our flow test results. So here we've got 1 3/4, 2.5, and 3 inch hose across varying flow rates, and we've got all the different mathematical methods that IFTA tells us we can use. So if we look at our flow rate on 1 3/4, our official formula tells us at 180 GPM, our official formula tells us 50 PSI friction loss per 100. The hand 12 tells us 50, the hand 9 tells us 36, the drop 10 tells us 31, the manufacturer tells us 30, we got 36. So on 1 3/4 and 1 3/4 alone, the drop 10 method happens to closely match our flow test results, but I promise you that's dumb luck. I don't know why it does, it just happens to do it. But on 2.5, we see at 300 GPM, the official formula tells us 18, the drop 10 tells us 20, which is pretty close, right? That's why we can use the drop 10 as an acceptable math method. Well, we got 13, which is pretty far off from 20. If we look at 3 inch, at 500 GPM, the official formula tells us 20, the drop 10 tells us 20, which is right on, right? But our flow test, we found 15, and that's due to that mystery hose. So some people might argue that a few pounds doesn't make a difference. Well, let's examine that. If we look at a 300-foot, 2.5 inch pre-connect with an 1 1/8 tip, this is not some mystery hose line that we're never going to pull on a fire. This is the pre-connect that's attached to our engines right now. So with this line, we've got a flow rate at 266 GPM with an 1 1/8 tip and 300 feet of hose down. We have 50 pounds at the nozzle. Now we have to determine our friction loss. So we start with our drop 10, we take our last number away, we get 26. We take away 10, we get 16 PSI per section. We plug that into our hose line. We have 48 pounds lost due to friction, plus 50 pounds at the nozzle, which gives us a line pressure of 98 pounds. If I use the numbers from flow testing, and here's our 2.5 pre-connect chart, which we'll go over later, I found that I have 11 PSI per section, not 15 or 16. So let's plug that into our equation. So we take away the 16, we throw in 11, which gives us 33, not 48. 33 plus 50 is 83, which is what our new chart tells us. 98 minus 83 is 15 pounds. So we're over pumping this line by using rule of thumb by 15 pounds. Where does that 15 pounds go? Into the nozzle, which increases two things. What? Nozzle pressure, three things. Our what else? Flow and our nozzle reaction, exactly. So this 15 pounds goes straight into the nozzle, giving us a nozzle pressure of 65 pounds. So what does that do? It makes a difference. So this is only a 15 PSI difference. Has anyone ever heard, oh, 15 pounds doesn't matter? Well, let's look at that. So an 1 1/8 tip at 50 PSI is 266 GPM with a nozzle reaction at 99 pounds. That's a 3 firefighter line. An 1 1/8 tip at 65 PSI increases our flow from 266 to 303, which is a 37 GPM increase. Our nozzle reaction goes from 99 to 31, which is a 31 pound increase or 30%.
130.
What did I say,
From
30?
99 to 130.
Yeah, 130 pounds of nozzle reaction. That's substantial. That's a big difference. So 15 PSI makes a big difference. This is why we use the numbers on the charts. We flow tested almost over a mile of hose to get these numbers. They're the single most accurate numbers we can use to ensure accurate flows and pressures. So what that means is once these charts go on the engine, no more drop 10 method, no more of the rules of thumb,
Yeah.
and like no more 100 PSI for the nozzle. Use the numbers off the charts. The next thing we got to do, now that we've charged a hose line accurately, we need to determine accurate flows of the pump panel. One way we can do this is by watering the grass. Right now we're just bleeding the air, right? But what we need is an accurate flowing pressure to make sure that we've got a set flowing pressure. This is the DO's chance to set a flowing pressure. So let me explain this a little bit. So an 1 3/4 pre-connect at 180 GPM has a target pressure of 130 PSI. So let's say my firefighter pulls the line and I go to 130 PSI on my discharge gauge. I verify that while they're flowing water. Because what happens when they slam that nozzle shut? What happens to my pressure gauge? Right, so they slam the nozzle shut, the pressure goes up, right? Because that hose line is storing pressure, all that, it's now expanded and it's now squeezing on that hose line, increasing the pressure in that hose line. So now I look back at my pump panel, I see that I'm at 150, I should be at 130, and I start either decreasing my engine RPM or gating back in order to control that line, right? They start flowing again, and because I did that, now my pressure goes down. That's one of the reasons why setting a flowing pressure is so important. If you set a flowing pressure, you know you can trust it, so when you see that spike later, you can realize what's happened. Putting a second line into service is even more important than we water the grass. So if I have a target discharge pressure of 130 PSI, and then I put a 2.5 in service at like 80 PSI, when I start opening that valve, because the water's not flowing, I'm gonna get a static pressure on that second line. So it's immediately gonna be 130. It's not gonna be until they open that nozzle that I can set a flowing pressure and gate it down to that 80 where I need it. So watering the grass is a good 4, 5, 6, 7, 10 second flow out of that nozzle so that the DO has a chance to set a flowing pressure. So we need to make watering the grass part of our culture. We need to train on it every time we pull a hose line. And what it is the DO and the firefighter working as a team. The DO needs to know that that's coming, and the firefighter needs to provide the opportunity for the DO to set the flowing pressure. So firefighters, when you pull that line, give it a good 5 to 10 second flow so the DO can get that flowing pressure set. We're gonna practice this in November, and we're encouraging crews to practice this when they go out. The last thing we're gonna talk about with friction loss is our 2.5 and high-rise problem. We discovered a problem, it was outside of our scope. Thanks. So 2.5 inch hose and high-rise hose had the widest friction loss variant across any of our flow tests. So it's a problem that we need to address. We need to get some different hose that has less friction loss variance. We discovered the problem, but it's a really expensive fix and more research is needed. Luckily, the high-rise committee is already on it. We're looking at possibility of a 2-inch solution, which is what Hal was talking about earlier. Maybe a dual-purpose hose load. And this is going to be a large expense. So the high-rise committee has slotted $55,000 for next year to get new hose and new equipment. That's in next year's budget, assuming it gets approved. So we'll be changing out our high-rise hose. And the cool thing is that that's going to a high flow rate model, so similar to a 2.5. So we'll do extensive testing on that hose, and we'll use that same hose on our 2.5 inch pre-connect once we get it. This will be part of the 2017 major emphasis training. Cool, so we'll take a 10-minute break. If captains, please be sure your crews are in back. We've still got a lot to cover. So I got 9:50, let's be back at 10 o'clock, please.
That's 9 minutes.
Yeah, they can definitely hear what you two are saying.
Yeah.
All right, so welcome back. Just reminding you where we're at in the class. We talked about nozzle pressure, how our nozzle pressure on automatic nozzles changes based on flow, which is why we use the number on the charts. We talked about friction loss, how our friction loss is not accurate because of mystery hose, so we have to use the number on the charts. Now let's talk about appliances. And there are some really great questions on brakes, which thanks for asking, and we'll get to some of that here. So we lose 10 PSI friction loss per appliance. We found that true in our flow tests. That includes a Y, a Siamese, a reducer. We definitely found that to be true during our flow tests. We lose 25 PSI for a street set, which as a reminder is not a blitz fire, and as another reminder, we have street sets. I know a lot of people think we've gotten away from those. Tyler, can you tell us what engines those are on now? I know 10, 5. And any of the nozzles, any of the master streams that don't have the automatic control, the remote, can be detached. So we've got more of those back in the system, and that's just a reminder that we have them. A blitz fire is not, it's kind of a wimpy monitor. It's not really a true street set, 500 GPM. It can be used as a monitor, but it's not like a true high flow street set. We lose 25 PSI friction loss for a street set itself, but that's not the blitz fire. The blitz fire, like an automatic nozzle, the friction loss for the device itself changes based on flow. So the nozzle pressure that you see on the charts for the blitz fire are at 500 GPM, and they already include the friction loss for the device itself. So while we're talking about blitz fires real quick, the blitz fire nozzle, that max force nozzle is a dual pressure nozzle. It switches between standard and low pressure. But at 500 GPM right here, this is the same chart we were looking at for our dual pressure nozzle on our 1 3/4. This is just for the max force nozzle that's on our blitz fire. So we see our separation between standard and low pressure, but at our max flow, we've maxed that spring out, whether we're in standard or low pressure, just like we would on an 1 3/4 nozzle, and the nozzle pressure remains the same. So standard or low pressure at max flow doesn't matter on the blitz fire. Reach, once again, a reminder, we have increased reach with our automatic fog nozzle versus our smoothbore tips. Once again, these were with stream straighteners.
Keep in mind, this doesn't really account for a significant amount of wind. We're not sure that a solid stream might carry further if it was windy enough.
Because we have a larger water droplet. Point being on this, there really isn't many situations I could even think of where you would want to put a smoothbore nozzle on a Blitz. It's actually against the manufacturer's recommendations for the Blitz Fire itself. So the point is just use the fog nozzle that's on there, try to steer away from the stack tips. Stack tips to get the proper flow in a stack tip, we have to pump it at the right pressure, which can be, difficult given mystery hose and all the other variables. So it's just a lot easier. We have great reach with that Blitz Fire, so just use the automatic fog that's on there. Remember, these are 500 GPM max nozzles. Remember that they have an automatic shutoff. So if you are using it as a remote monitor, say to cool tanks or something like that, you might want to tie back that automatic shutoff, that handle, so that you can use your valve at the engine to turn it on and off. Because if you use your valve to shut it off at the engine, I guarantee you that automatic shutoff's going to engage and you can no longer engage it remotely. Just remember, if you're doing that, you're technically disabling a safety mechanism. So use good judgment, tie it down well, all that good stuff. So back on the topic of appliances, supply to Ys, meaning basically extending a line with a Y, have some interesting hydraulic anomalies. So let's talk about that. So if I run 300 feet of 3-inch to a Y at 180 GPM, I need to figure that out hydraulically, right? So at 180 GPM through this line means I have 180 GPM thrown through my 3-inch. These are the new numbers for friction loss on my 3-inch. And I find I lose 3 PSI per section, which gives me 9 PSI friction loss for 300 feet. Everyone follow me so far at 180 GPM. If I put that second line into service, I add another 180 GPM, which increases my flow to 360. So now I need to increase my friction loss, increase my pressure to account for friction loss when both lines are flowing. So per my chart, I lose 8 PSI friction loss per section. I plug that in and now I'm at 24. So when one of those lines shuts down, I have 9 extra pounds in the nozzle. So when I shut down one extra line, my 9 from before gives me an extra 15 PSI. Where does that extra 15 PSI go? Into the nozzle, which increases 3 things. Nozzle pressure, reaction, and flow all go up. So we'll see exactly what that looks like for our flow test in a second, but we're going to watch a video that demonstrates this. Is the sound up?
Okay, scenario number 3 is 300 feet of 2.5 to a gated Y, 2.5 to 1.5 gated Y to 100-foot hose pass. My pressure is set at 140 at the discharge, and we're looking at what kind of change do we get in nozzle pressure when one line shuts down.
This goes a little bit to what you were talking about earlier, Adam.
So with 2 lines flowing, our nozzle pressure is 52. Phil, go ahead and shut down.
Watch that gauge.
We spike to about 90 and it's settling about 85. Phil, go ahead and open it again. And we drop back down to a nozzle pressure of 52, 54.
Now they're seeing a pretty wild spike due to their hose line configuration. I don't know what their flow rate was, and exactly, they had only 100 feet down, so we're seeing a greater increase of this. But we flow tested our equipment with this to find out what would happen. So this is Y operations with 2.5-inch supply. So here's our 2.5-inch supply to 2 3/4 lines. When both lines are flowing, they're both at 180 GPM, 67 pounds of nozzle reaction, everything's great. When we shut one line down, our nozzle pressure increased from 60 to 75. Our flow increased from 180 to 215, and our nozzle reaction went from 67 to 94. Look at your chart. How many lines is that?
How many
firefighters is that? 3, right? So we've gone from a one firefighter line to a 3 firefighter line just by shutting down a nozzle.
And keep in mind, you don't know that's coming.
Yeah. So that's he might be on the other firefighter might be on the other side of the house. You have no idea that's coming. So one thing we can do to help mitigate this is increase our supply hose from 2.5 to 3-inch. So when we do that, once again, we're balanced when everything's flowing. In the last test, our pressure was 75. In this test, our nozzle pressure was decreased to 65. In the last test, our flow was 215. Now we're at 210 because we have a slightly decreased flow and a substantially decreased nozzle pressure. Our nozzle reaction goes from 94 in the previous test to 84 here. So we do, 85, sorry. So this is still a 2 firefighter line, but we've decreased it by 10 pounds, which as we've learned is substantial. We'll talk about that more in a little bit. Another thing we've seen people do, and may or may not be a tool in some people's toolbox, is creating a manifold out of your Y. So this is the supply to Y, right? So you have a supply going to a large diameter Y to a smaller diameter Y, and then putting a reducer on the other side. So you're basically throwing 3 lines off of one supply. So first off, with this test, we should be flowing 540 GPM, but our flow meter and our supply on this day had a hard time giving us much more than 480. So these numbers should be higher than they are right now. The first thing to notice is our discharge pressure of 250, which is very high, too high. Next, when you shut these lines down, our flow goes from 180 GPM to 245, and our nozzle reaction goes from 67 to 122. A 2.5 with an 1.125" tip has a nozzle reaction of 99 pounds. So by shutting both those lines down, you've turned that one line into something more substantial than a 2.5.
A 2.5 with an 1.25" is 123 pounds.
So that's substantial. So for that reason, we're eliminating this option at PFA. This is not safe no matter how you slice it. There's a lot of people that advocate completely eliminating Ys. They cause pressure spikes, and the other problem is that if your supply line fails, you've now lost both your lines. So do you truly have a backup line when you're running a supply to a Y? Once again, like everything else with this, we have to look at PFA. Y operations have a very positive effect on our operations. We have a lot of alleys in Old Town. We have a lot of Prairie mansions out east that might have 200 feet from the driveway to the front door. We have oddly configured apartment complexes, long lays to the backs of houses. And we have to look at our staffing. What non-Y advocates say is you should extend every line to eliminate these hydraulic variables. So you can imagine how much more time that would take extending every single line versus just running a supply to a Y. So once again, we have to look at the problem in its totality and realize the best way to mitigate it. So what we've come up with, the Y rules at PFA, these are currently going through the OD committee. They're written in the DO manual, and we'll be sending those out for feedback soon. But PFA only uses 3-inch hose to supply a Y, not 2.5. So once again, we're decreasing our total line pressure by doing that. Were you running 2.5 or 3-inch when you were doing it?
3.
Okay. As a reminder, this is kind of advocating for 3-inch to be our supply, not 2.5. So 2.5 is an attack line hose, 3 inches is a supply hose. That includes going to a blitz fire. Dual Ys, so this is the manifold setup I was talking about earlier. Big water hand lines, which would be putting like 2.5s off of a Y, which you can imagine, we didn't test it, but you can imagine higher flows, what the effect that would be. And different line pressures off a Y, so running like a 100-foot pre-connect and a 200-foot pre-connect off a Y because we've got differentiating nozzle pressures, which would be gating back at the Y. So all those options, we're eliminating those from our toolbox. So put simply, PFA uses 3-inch to supply to a Y with a maximum of 2-inch and 3/4 hose lines of equal length attached to the Y. Does that make sense? Super simple. This is what it looks like every time. 3-inch supply, 2-inch and 3/4 pre-connects. Of course, we could use 100-foot hose packs if we want on the end of those, but if we did that to one side, we would also want to do that to the other side. The nice thing is, by standardizing our deployment on this, it can standardize what we call it. Because right now, what do we call this? An alley lay, a low rise,
Yeah, horizontal high rise.
horizontal high rise, a extended lay. We've got 1,000 different things we call this. It's a supply to a Y. Engine 10's on scene. We'll be resetting the fire on the Charlie side with a supply to a Y. Everyone knows exactly what that means. The next engine company probably is going to be hooking up to the end of that. We've
They
got
should be bringing their pre-connect, not their high rise.
right. Now we have to use common sense in order to apply this, right? So we know we have a hydraulic problem with this. We have an increased nozzle reaction when one line shuts down, right? We've gone from 67 pounds to 84 pounds of nozzle reaction. So captains can be heads up and back their firefighters up a little bit more when they know they're running off of a Y. That's one thing we can do to help mitigate that increased nozzle reaction. Another thing, we have to apply common sense. If we're standing on ice, we're up on a roof, we're on a ladder, it's probably worth extending that line because in those situations we don't want to deal with an increased nozzle reaction. Does that make sense? So we got to apply these principles with common sense. Another thing to consider with this is most of our engines only have 2 200-foot pre-connects for their 1 3/4. So if you're arriving on scene at a fire, grab your pre-connect and bring it to the fire because you don't want to hook the high-rise hose up One of the reasons, because we're going to be switching to our 1-inch tips on our high-rise packs, which we're going to talk about later. And that would be differentiating pressures off of Y, which we don't want. So that makes sense? So what do we call it? Supply to Y, good. So last thing we're going to talk about in the conversation about total line pressure is elevation. So elevation, as you stack water vertically, gravity affects force on the water, and that force is equal to 4.34 psi per foot. 0.434 psi per foot. We round that to a half a psi per foot, which is convenient because you just have to take half the height. So if I pump water up a 30-foot hill, I divide that by 2, and I've got 15 psi that I have to add to my line for the correct pressure.
To overcome head pressure.
To overcome head pressure. If I pump water downhill, head pressure adds pressure to my line pressure, so I would take that away. So if I pump down a 30-foot hill, I would take 15 psi off my line pressure. If I'm thinking about it in stories, I take story minus 1 times 5. Here's how we get there. We have 10 feet per story on average, so we figure that out ahead of time. 10 times 0.5 is 5 psi per story, right? The reason we take a story away, if I'm on the 3rd story of a building, I'm standing 20 feet off the ground. I'm not standing 30 feet off the ground. So it's story minus 1 times 5. Does that make sense? Okay. So we've talked a lot about line pressure, how important accurate line pressure is so that we have an accurate GPM. So the second part of this conversation is looking at our hose line deployment as a whole, right? So we've got a lot of options right now, and we can really simplify our hose line deployment and still be effective. So we're gonna use 2 concepts to drive this conversation. The first one is the box idea, which is that a known GPM puts out a known BTU or a known volume of fire. And the standardized weapons idea, which is kind of standardizing our hose line deployment and getting everyone on the same page. So this is that forcing the door with an axe versus forcing the door with an axe and a Halligan analogy I was using earlier. Right now we've got a ton of options. We have standard pressure, low pressure, different size stack tips, different hose sizes, smoothbore versus fog on a master stream. What are we doing in high rise? We've got a lot of options. So we can really simplify this. And the point is we can simplify it and remain effective. We can be effective and simple. We don't have to sacrifice effectiveness for simplicity. What drives this is flow rate, and this is what we were getting at during the break, Kevin. Flow rate is GPM versus BTU. It's the amount of water you need to use to overcome flashover. All of our data is telling us that we're arriving at or near flashover, right? So the point is to control flashover. As a reminder of how fast flashover can occur, that's 1 megawatt of energy, which is 1 recliner. So flashover can happen very, very quickly. 2 megawatts of energy equals a couch. So flashover, once again, can happen very quickly. So we want to control flashover, right? We're already doing that. Door control is a step we've taken to PFA in an attempt to control flashover, right? That's directly related to firefighter safety. Another thing we can do is put water on the fire, right? And decrease the temperature and help control flashover. So NFPA recommends 150 GPM to do that. The way they state it in their standard 1710 is your first 2 lines of a fire should equal 300 GPM, with your second line not being smaller than your first. So that's one of the reasons we landed on 150 GPM. We used to have a lower flow rate, which is why we used to use 1.5-inch hose. As we increased our flow rate, we reached critical flow on our 1.5-inch hose. We needed to increase our hose diameter to 1.75 inches. So there's a lot of research out there talking about increasing a flow rate. One of the reasons is that 180 GPM is a lot more effective against flashover, and the other reason is if I walk in the door with 150 GPM and I go up a flight of stairs or I get a kink in my line, I've decreased my line pressure, which then decreases my flow rate, right? So if I get a kink in the line, I'm no longer at that 150 GPM minimum. If I walk in the door with 180 GPM, and the idea is to kind of walk in the door with the highest nozzle, the highest flow rate that you have with the lowest manageable nozzle reaction. So remember, we want to stay under that 70 pounds of nozzle reaction. 180 GPM is right at 67 pounds of nozzle reaction. So we're effective, and we're effective against the fire, and we're also effective with the amount of nozzle reaction that we're using. So 180 GPM is our new target fire flow on 1.75 inch. Am I missing anything on that? Yeah. We talked a little bit about kinks. Let's talk a little bit more about them. The rule of thumb is that 1 kink equals a 10% decrease in flow. We pretty much found this to be true in our flow tests. One 90-degree kink was a 10% decrease in flow. One 180-degree kink was a 20% decrease in flow. And two 90-degree kinks was not 20, it was a 30% decrease in flow. That's substantial. Hal, you got the numbers on that?
I'm good.
Okay. So, you know, if I walk in the door with 180 GPM and I lose 10%, I've lost 18 GPM. I'm still above that 150 GPM minimum. So we have to manage kinks.
So if you have two kinks in the line, you're down at 126 gallons,
Starting at 150
starting at 180.
at 180. So two kinks in the line is substantial.
So kinks are a much bigger deal than people realize.
That goes right back to those line of duty deaths out of Oakland and Fresno. This is some of the stuff that was contributing to their lack of fire flow, and they're taking the bullets out of their gun, right?
Fresno had 95 gallons per minute, and if I remember right, Oakland was at 100 gallons a minute.
Right, and they thought they were pumping at 150. So we have to manage kinks. The first step of that is good hose deployment, right? Get our hose down on the ground in a way that it doesn't kink when we charge it. Thinking DO can overpressure that line initially to help push those kinks out and then reduce to the correct line pressure. This is one of the best things we can do against nozzle reaction, but against kinks, is hammering the nozzle. Just taking that nozzle and just hammering it open and shut. It is really effective at pushing kinks out. There can be concern with this about water hammer on the pump, right? So we've talked to waterists, we've talked to the nozzle manufacturers and the hose manufacturers, and nobody's worried about it. We're only flowing a tiny little bit of water as we're doing that, so we're not creating a huge mass of water that's going to impact the pump. Our velocity is also very low because the water's not reaching velocity before it leaves the nozzle. The last thing is that hose jumping around, pushing the kinks out, that 200 feet of hose is dissipating that energy, so that energy isn't impacting the impeller or the pump components. We might have to manually fix kinks. We have to manually fix kinks, and that's everybody's job on the fire ground. No one should walk past a kink on the fire ground. That needs to be a cardinal rule here at PFA. I don't care if you're a safety officer, a chief, a truckie. I don't care what your role is on the fire. If you see a kink, fix it. You don't even need to break stride most of the time. You can just kick it out and keep walking. It literally takes 2 seconds. Nobody should walk past a kink in the fire ground. We can account with an increased flow rate for a kink that is unbeknownst to us if we round a corner in the line kinks. It's gonna happen, right? We can account for that. We cannot account for the 3, 4, 5 kinks that are sitting in the yard. I know some people griped when we got rid of those Gassner loads that we had on the engines. How many kinks were on those Gassner loads every time you charge them? A ton, right? So we talked about flow rate and kind of that our increase to 180 GPM. The next part of this is the box idea. The box idea is that a known GPM puts out a known volume of fire. To determine this, we can use the NFA formula. There's a couple different formulas out there. There's the Iowa formula, which really has to do with total GPM applied in smaller droplets of water.
Unventilated structures.
In unventilated
And
structures.
basically shipboard firefighting.
Right. So it can be effective, but with the NFA formula, to determine our flow rate, we take the area, we divide it by 3, multiply that times the percent involvement, and that gives you your GPM needed. That's a whole lot to do at 2 in the morning, so let's look at this. So let's say we have a 25 by 50 foot house, 30% involved. What's 25 times 50? Determine the area. Quick.
25 by
Engines.
50.
What is it?
1250.
1250,
Yeah,
right?
very good.
That's second fastest we've seen.
Yep.
So divide that by 3. Quick, units are arriving on scene. Babies are dying. What's your flow rate at this fire? 1250 divided by 3, quick. 4 something,
Pretty
right?
close.
416, pretty close. Times our percent involvement, 30%. 416 times 30%. Quickly, what's our flow rate? What's our flow rate?
26.
There it is, 124. Pretty good, right? That sucks, right? That's a lot to do at 2:30 in the morning after you just woke up. That's no fun, right? Ooh, preserved in video forever. So anyway, let's simplify this. The box idea simplifies this. So we know what our target flow rate is, right? We know what's effective against flashover. 180 GPM is effective against flashover. So let's figure out how much fire that puts out. So when we reverse that, we find out that 180 GPM puts out 530 square feet, which is about 23 by 23 feet. What else is 23 by 23 feet? A 2-car garage, a standard living room. Those are all things we can identify very, very quickly, right? So when we arrive on scene, we can just say how many 2-car garages on fire and use that to determine our flow rate. Does that make sense? So if we've got a 1,000 square foot house and 1 inch and 3/4 puts out 530 square feet, how many 1 and 3/4 lines does it take to put that fire out? 2, right? 1 2-car garage, 2 2-car garages. Does that make sense? We're gonna practice this. If I've got a 2-story house and I've got 2,000 square feet, I've got 2 2-car garages on the lower level and 2 2-car garages on the upper level. All I gotta do if I'm looking at like a larger handline, like a 2.5, is use a bigger box. And we're gonna talk about that. We've got point of references for this. So the standardized weapons idea is basically knowing what tools you have and then using the right tools for the job. Known tactics applied to a known problem equals a known outcome. This is all delicately balanced scale. The fire service didn't just land on 1 3/4 and 2.5 inch hose by accident. 1 3/4 gives us the desired flow rate with a manageable line, right? Because we have to include mobility, flow rate, all that kind of stuff into that. 2.5 is our next line size. You know, like I talked about earlier, 1.5 inch hose was common. We increased our flow rate. We are now at critical flow, so now we needed to increase to 2.5 and 1 3/4. The reason we use these hose lines is we're still maneuverable. We have good hose diameter to weight ratio, and we have enough GPM to put the fire out. The biggest factor that goes into this is nozzle reaction. There's 2 nozzles that give you this flow rate on 1 3/4 hose line, and that's a 15/16 smoothbore or a low pressure fog nozzle. Both those give you manageable nozzle reaction. We have low pressure fog nozzles, we just got to use them in that setting. So to apply this concept, this right here, this chart, and there's another part of it, which I'll show you in a second, sits right here on our pump charts, so everyone can reference it whenever they want. It's also in the DO manuals, and it's also on the handout sitting in front of you. We really want to get these numbers in people's heads. Like I talked about, we can be simple and effective. We've basically got 5 options at a structure fire. We've got 2 offensive hand lines and 3 defensive lines. Our 2 offensive hand lines are 1 3/4, 180 GPM. We have an 1.1/8 tip on our 2.5 at 266 GPM. At this point, we've reached that law of diminishing returns, right? We've increased our flow to the point where it's now a defensive line. We're above 300 GPM. So we unscrew that 1.1/8 tip, we're left with the 1 1/4 tip on our 2.5, which increases our flow to 328. Our next option is our blitz fire, and then our deck gun, aerials, and street sets. So that's it. Those are the options we have at a fire. So all we got to do is figure out how much fire those put out and apply those principles on a fire. So let's practice doing that. So here's what these lines can put out. We've got 2 structured fire hand lines. We've got 1 3/4 at 180 GPM. That's a 23 by 23 foot area. That's about 530 square feet. That's a 2-car garage. That's a large family room, right? That's our primary weapon. It's our assault rifle, right? We have good stopping power and good mobility. So on a fire about this size, we have maybe 700 square feet up here. So 2 3/4 will put that out, no problem. With the volume of fire we're seeing here, 1 3/4 should handle that, no problem. And you probably don't need 600 feet of hose on the front lawn, but they felt like they needed it. So our next weapon of choice is our 1 1/8 tip on our 2.5. That's 266 GPM. That increases what we can put out. It goes to 28 by 28 feet, which doesn't seem like that big of an increase. But that goes to 780 square feet, which is 250 more square feet, and that's substantial. This is great for commercial fire or a big water reset. Big water reset is where you show up to a large volume of fire, you pull your 2.5, you extinguish that fire, you switch to your 1 3/4 and go in for your direct attack. At this point, we've reached the law of diminishing returns. We can increase our flow rate and remain mobile. So now we've gone defensive, which is where we go to our 3 defensive options. But this right here is our light machine gun, right? We can bipod up and use this, so we're not gonna be really flowing and moving with this. We can flow, stop, move, flow, stop, move. Stop, flow, move, sorry. So if we show up to something like this, we can get a nice big water reset very quickly. It's pre-connected on our engine, and then we can move in with our 1 3/4 and remain mobile. So now we've reached that law of diminishing returns, and now we're increasing to defensive lines. We've really got 2 mobile options. We've got an 1 1/4 tip at 328 GPM. So remember, that's unscrewing that 1 1/8 tip, going to 1 1/4.
Just as a point of reference, earlier when you talked about the master stream versus a hand line, going from 350 down to 300, that's a 25-pound nozzle reaction difference between 300 and 350.
Right. That's a 31 by 31 foot area, which is 960 square feet. That's almost 1,000 square feet. That's substantial. That's a lot of fire that you can put out with still a mobile hand line. But we're not going to be flowing water and moving with this. This is truly transitioning to a defensive line. So we're going to be throwing a loop in this, sitting on it, or something like that. This is our somewhat mobile attack line. We can post up, use it, and then it takes some effort, but we can move it again. So once again, some sort of big water reset. Next, we move to our blitz fire. That's our second defensive line option. That's our fog nozzle at 500 GPM. That's a 40 by 40 foot box, which is 1,600 square feet. So that's a substantial amount of fire that blitz fire can put out. That's gonna be our mortar, right? We can set it up, we can deploy it, we can use it, we can move it again, but it takes some work, right? Not as mobile. So if we see a volume of fire, something like this, that would be appropriate for a blitz fire. So if we've got a huge volume of fire, we obviously bring out our heavy artillery, which is gonna be our deck gun, aerial, monitor, and street set. Don't forget that deck gun's an option. We don't always have to set up the aerial. That deck gun is a great tool. So the point here is we can be simple and effective, right? So here's the full chart now, looking at everything that you have in front of you on the DO manual, on the pump charts. We've got 2 offensive lines and 2 defensive lines. We've got an 1 3/4, 180 GPM, 23 by 23, 530 square feet. That's our 2-car garage. We've got an 1 1/8 tip at 266, increased to 780 square feet. Our box is now 28 by 28. We go to our 1 1/4 tip, 328 GPM, 31 by 31. That's almost 1,000 square feet. And last, our blitz fire at 500 GPM, 40 by 40, or almost 600 square feet. So those 4 line options, of course, our deck guns, aerials, and street sets. But those 4 line options are really our bread and butter on 99.9% of our fires. And now those are what the pump charts are designed to help us pump. Using these ideas helps everyone. It helps command and captains by determining what line they need to put in service and when. It helps DOs. If you can pump these 4 lines and a supply to a Y, that's 99.9% of everything that we're gonna pump. So we're really trying to get out of that habit of these like crazy exotic hydraulic problems that we give DOs. We wanna be really good at the stuff that we do all the time. And that's what these charts are designed to help us with. It also helps firefighters. If I can pull the 1 3/4, the 2.5, the blitz fire, and a supply to a Y, if I can pull those 4 things, I can be extremely fast at those 4 things, and that's all I really need to be good at, because those are the options on a fire. So now we also have to use depth of knowledge and common sense to apply these principles. Things like tight access, landscaping, and our staffing can change what we're wanting to do. So let's say I show up at a fire that has a volume of fire over 1,600 square feet that's gonna warrant a blitz fire. But I've got crappy access, I've got a fence in the way, I've got a lot of landscaping, I've got a building right in the way, then I might opt for a lower flow rate at a higher application time for increased mobility. Does that make sense? We're gonna practice with these. So we're gonna do some practice with this. There's no right or wrong answers here. We're just gonna practice and discuss hose line selection. Don't get too bogged down in the details in the picture. We're strictly looking at volume of fire and line selection and application rate. Assume you have a water supply or are getting one very quickly. So here's our first fire problem. How many 2-car garages are on fire? 2, yeah? We can all agree with that. What would be some good line selections with this? What are our options?
2 3/4.
2 3/4 would put this out, right? What about a 2.5? Would that be effective here? Sure, right? So now we have to start applying common sense and depth of knowledge here. We probably are compartmentalized here. We've probably got a wall running right here separating both of these. So we're no longer talking about free burning of two 2-car garages. We're talking about 2 different 2-car garages. Does that make sense? We're compartmentalizing that. So we could be more effective with an 1 3/4 here and here, right? If we took a 2.5 on this, we're gonna hit this side, then we're gonna have to drag that 2.5 and move it over here. How many people is it gonna take to drag that 2.5 and move it over here? It's gonna be a lot more work, right? If we have to look at our staffing, that goes back to that staffing question that we had. We can throw 2 firefighters on 2 1 3/4 and they can both move independently and get the water where we want it. Does that make sense? No right answer, those are just looking at our different options. So this is kind of the mental rep that we want to do when we arrive at a fire. How many 2-car garages on fire? And then what staffing do I have to support the most efficient hose deployment? So I've got 2 2-car garages on this. Does that make sense? So kind of get these slides in your head when you're thinking about this. If I use an 1 1/8 tip, that's 780 square feet, 28 by 28. My 1 1/4 is going to take care of that entire area at almost 1,000 square feet. And my blitz fire is going to take care of its overkill, but we're just kind of seeing what the idea is like. How many 2-car garages are on fire? 1, right? Right about in this area right here. There's our 1 2-car garage. There's our second 2-car garage. What if it was just this area up here? How many 2-car garages would be on fire? Half, maybe 1. We're just saying we're taking the same principle and we're just applying it to the second floor. Does that make sense? Then we have our engine 8th tip, 266 GPM, 780 square feet, 28 by 28 foot box. Our almost 1,000 square feet, 1.25 inch tip, and obviously overkill for this, but our blitz fire is 1,600 square feet. How many 2-car garages are on fire? At least 2, maybe 3, could be even 4, depending on how deep that goes. This is a big building. Look at how deep that goes, right? So if we're using the NFA formula, we're like, I don't know, 75 feet by 40 feet. Who knows how close we are? We can look at this in chunks and say there's probably 4 2-car garages on each level here. So we're looking about 2,000 square feet per level. So if we've got 2 2-car garages up here, 2 3/4 inch would take care of this. What are our other options here? 2.5, right. So let's say we've got 3 2-car garages on fire. How many square feet is that? 1,500, right? What's our 1,500 GPM? What's our 1,600 square foot line selection if we look at our chart? Blitz fire, right? So we've got a volume of fire that's probably calling for a blitz fire here. Does that make sense? Is a blitz fire a good option here? Not a trick question. Yeah, right? We've got plenty of room to deploy it out here. We've got a nice big front yard. What if we had really crappy access? What if we had another house right here? Would a blitz fire be a great option? Somebody said nope. Why? Discussion, you guys can say it. You know the answer. Angle, right? Probably can't get the water where you want it, right? Those blitz fires have a stop at the top and a stop left to right. Plus, they're hard to move around. So if you threw a blitz fire on this with crappy access, it's going to be more challenging. Does that make sense? So here's a volume of fire. I think we can all agree a big water reset is going to be a good choice, right? Using the 2.5 with either our 1 1/8 or 1 1/4 inch. So let's take that same volume of fire, let's compartmentalize it, and let's give it bad access. So where we've got 2 2-car garages worth of fire, so we're looking at, an 1 1/4 inch tip for that. Let's say we've got two levels of fire, a 2-car garage stacked on top of a 2-car garage, so we're compartmentalized, okay? So now we've got crappy access. We've got this fence that's maybe 10 feet off the building. We've got our engine here. We've got about a 300-foot lay if we're going for a Charlie side reset, which let's say we're doing for whatever reason. So we've got a volume of fire. It's about 1,000 square feet, which is how many 2-car garages? 2, right? So our most practical line selections are going to be what? 2 3/4 or
1 1/4 tip.
1 1/4 tip. So what's going to be more practical? How are we going to get water on that fire? We have to look at our staffing, right? So what are our options here? We got a 2.5 or 2 3/4. How can we get 2 3/4 back there? Supply to a Y, right? That'd be a great option. If you get a 2.5 back here, you're only putting, remember we're compartmentalized. We've got 2 2-car garages that are stacked, right? So if you get 2 3/4 back there, you can do that quickly. B, 2 firefighters can each direct their hose stream in the compartmentalized fire and take care of it probably a lot quicker than 1 2.5 and lugging that around. Does that make sense? So we have to look at our staffing and apply that. How many 2-car garages are on fire? 3, maybe 4. Let's compartmentalize it. How many 2-car garages is that upper level? 1, maybe 2. What about down here? 1, maybe 2. Let's take this out of it. So let's say once again we've got 2 2-car garages on fire, maybe 3. So we've got a volume of fire here that I think everyone could agree we're going to throw a blitz fire at. Can everyone agree on that? If we look at volume of fire. So let's take a volume of fire that would call for a blitz fire and let's give it poor access. So these are the Brooklyn Park row houses in Station 10's area. The King Supers on Drake and Timberline is right here. So we've got row houses that are connected with fire separation. And we've got an alley that we can get down, but we're not going to be putting an engine down there with fire down there. So we're parking our engine out here, and we've got about a 300-foot lay to get back here. We've got a volume of fire that's calling for a blitz fire. But is a blitz fire going to be super practical here?
The ground level is garages.
Right. So we've got, is a blitz fire going to be practical here? Why not? Angle, right? It's gonna be hard to get the water where we want it. So we're looking at a 2.5. Is a 2.5 gonna be practical here? It's not a trick question. Probably is, right? 2.5 will be practical. We got a 300-foot pre-connect. We can get there pretty quickly, right? One thing to think about, we've got a volume of fire that's upwards of what a 2.5 can handle. So if we want to pull another 200-foot pre-connect, that means we're going to have to pull another engine up here to get their hose pack to pull it. We've already got 2 inch and 3/4 hose lines on this engine, so another option is what? Supply to Y, right? Does that make sense? Kind of getting the idea? So you can hit the lights out. What we're asking everyone to do is just practice with this. So like when you guys are watching your YouTube videos back at your stations, like everyone does to get their mental reps, add that into your decision-making model. How many 2-car garages are on fire? What's my hose line selection and why? And talk through that stuff. It gets super quick the more you do it. So now that we know the lines we use and how we use them, we need to be able to put them into service quickly. All of our data out there with all our fire behavior research is telling us that the number one thing we can do is put water on the fire quickly. That's one of the best things we can do. The new pump charts are designed to help everybody do that. So the new pump charts you see hanging up in the room are designed to reinforce everything that we've been talking about, and they're designed to make what we're talking about go into service quickly. They have very similar content to what's on our old charts. Table for table, they're almost exactly the same. There's just different numbers. The biggest difference is that we're getting our friction loss and our nozzle pressure from the charts as opposed to determining them by rules of thumb. So here's what they look like, right? We have those 4 line selections, right? We've got our 1 3/4, our 2 2.5s, and our blitz fire, right? And a supply to Y. These charts are designed to support that and give you that information quickly. You've got your 1 3/4 at 180 GPM with your flow rate. Remember, here's that chart we were talking about that has our flow rate and our box idea right on there. 180 GPM, our first line. Our second and third line are our 2.5 with an 1 1/8 and an 1 1/4 tip. Gives us a flow rate of 266 or 328 GPM. Our last line we can put into service is our blitz fire. 500 GPM and all the numbers associated with it. The only other thing we can run is a supply to Y, and if I'm running that, I get my 3-inch friction loss right here, or my deck gun, and that's easy because I just charge it 100 PSI and I'm pretty much done. Does that make sense?
Highlights will really help you.
Right. Everything that's highlighted is all the stuff that we're going to use mostly, and we'll go over exactly how to use this. We'll do a few examples for everyone, and then later the DOs, we're going to spend an hour just working these charts. I promise you'll leave here being comfortable using these new charts. So now that we know what lines we have and what they can be used for, we'll talk about how flow testing and some of the stuff we've learned in the DO Academy has changed some of our pump operations. What I'd really like to do in this class is to go straight to the charts and show you how they work, since we've been talking about that natural progression. But I want that to be the last thing the DOs see before the breakout session. So we're going to completely switch gears, talk about some new high-rise operations, and we're going to come back to the charts. The new DO manual has all this stuff in it. New things on valves, foam drains, cold weather storage, after pumping, relay, hydrant transfers, aerials. We're going to talk about some of that in the DO breakout session, but it's in the new DO manual. What we're going to cover today with everyone is going to be standpipes and sprinkler systems, and then our new pump charts, how we're using them. So, standpipes and sprinkler systems. There's a raging debate in the fire service for fog versus smoothbore. That debate does not exist when you hook up a nozzle to a standpipe. There's standpipes are just full of crud, debris, and all sorts of nastiness. Here's a picture of a crew flowing off of a standpipe. Look at this black water coming out of it. They deteriorate over time, they scale, they rust, there can be construction debris inside. So you imagine what that would do to a fog nozzle. We all agree that's probably not a great idea. Here's a piece of debris that came out of this 1 3/16 nozzle. Look at this right here. That's an 1.5 inch coupling, and that size of debris came out of that standpipe. Imagine what would happen if that got jammed up in your fog nozzle. So for that reason, pretty much nationally, no one even argues putting a fog nozzle onto a standpipe. It's smoothbore or nothing. So we're switching to our smoothbore nozzles after this. Once everyone's gone through this class on our high-res packs, we're going to switch to our 1-inch tips. Next year in the major emphasis training, we're going to get the new hose loads. This is definitely a Band-Aid. This is not ideal, but it's kind of getting the job done until we can fix it permanently. So fire pumps and standpipes, all buildings in PFA's jurisdiction, 4 floors and higher have a standpipe and a sprinkler system. And that's 4 floors or 40 feet. It probably has a fire pump. 9 times out of 10, it's going to have a fire pump. The only time it wouldn't, like if you had like a 3-story apartment complex that was sprinklered, The domestic water supply is probably adequate pressure, so it's only gonna have a fire pump if it needs to boost the pressure, but they've already predetermined that. A fire pump is part of a system that is designed to put that building out if it catches on fire, so we wanna use that system. The only exception, and I'll read it again, all buildings in PFA's district 4 floors and higher have a standpipe and a sprinkler system and probably a fire pump. There's 2 exceptions. Park Lane 1 and 2, which have a standpipe and a fire pump, but only have sprinklers in the parking garage. And DMA Plaza has a standpipe and a sprinkler system, but no fire pump. They're going through a retrofit. Do you know, Cap, if they've started that yet, that fire pump at DMA? I'm not sure. They hadn't as of a couple weeks ago. So fire pumps are designed, they're pre-engineered to give us the flow we need out of them. The kind of golden rule with standpipes and where we're going in the future with a higher flow hand line is going to be, they're designed to be used with 2.5-inch hose with 1.1/8 tips at roughly 250 GPM. So they're designed to provide 500 GPM, 2 hand lines at 100 PSI on the main standpipe at the furthest point. They're designed to give 250 GPM at 100 PSI on additional standpipes, so if there's other standpipes in the building. Both of them are always going to be supplied by the same FDC. The point here is let the fire pump do the work. They're designed to be part of a fire suppression system with our hose lines and hose packs in mind. So let the fire pump do its work. We don't need to go in and overcome the fire pump. Where there is a backup, but we don't need to be the primary. Pressure reducing valves exist in some jurisdictions, not in PFAs. Pressure reducing valves exist because a fire pump, you can imagine if I'm on the 1st floor, I'm gonna have a higher pressure than if I'm at the 10th floor because the head pressure hasn't come into play yet. So pressure reducing valves reduce pressure at the standpipe. We don't have any in PFA's jurisdiction. Those have failed in the past and been directly contributed to line of duty deaths, but luckily we don't have any. So this is kind of how we used to do standpipes. We have our 2 lines feeding our standpipe with our different hose lines. You know, we had to account, you know, these guys were operating at pressure, these guys were gaining back, but how and what pressure were they gaining back to? We had our line pressure, we had our friction loss for the 3-inch going to the standpipe. We had an appliance loss of 25, which never made much sense.
I have 2 examples for you. One is 4 floors, one is 6 floors, 4-inch pipe. In both cases, less than 1 PSI of friction loss. According to IFSA, they suggest using 10 PSI as if it's an appliance for the FDC.
So, you know, you have like a 4 or 5-inch pipe on a standpipe, you're only flowing 500 GPM. Through 4 or 5-inch pipe the friction loss is minimal. So how can you just say 25 blindly? And we already talked about how important accurate pressures are for a lot of different reasons. So we're switching gears with high rise. We're going to use pressure gauge discharge on the floor below the fire. We're going to regulate that pressure with a inline pressure gauge on the standpipe, and then the attack crew will call for more or less pressure if needed. So the standpipe, this will hook directly up to the standpipe. This is an inline pressure gauge. We're going to have this marked with the various different lengths, and basically what's going to happen is the attack crew will call for more pressure if they need it. So they'll hook this up to the standpipe. They'll charge the hose line, they'll water the grass. If they've got the pressure they need, that's great. We hooked up to the standpipe as a DO, and we're there as a backup, but the fire pump is probably gonna give us what we need. Does that make sense? So the attack crew is gonna hook up, they're gonna use this gauge and the gate valve on the standpipe itself to regulate their pressure. Does that make sense? So these are gonna get distributed after everyone's gone through this class. And then of course, we're gonna be using them next year with the new high-res loads.
So in order to get close, though, we're not figuring the 25 PSI in?
No, we're strictly, everything's going off that pressure gauge. Yep. Just like pumping the aerials, we're gonna be using the pressure gauge and the flow meter on the aerial to determine our flow, which is exactly what we're gonna be doing here.
Yeah, you end up way too high anyway. If you look at the chart for our 1-inch tips that we currently have, and then you did add that 25 PSI, I mean, you're quickly over 250 PSI.
Yeah.
Right. And then, you know, the DO is really, I mean, you don't, if without a pressure gauge on the fire floor, I mean, you can guess and do math all day, but you have no idea what you're pumping. So that's why we're going to the pressure gauges. And this is becoming a National Fire Service trend. So DOs, when you're charging the FDC, charge it at idle, recirculate some water, and you're there as a backup for the fire pump. So if the crew needs more pressure, you're gonna have to provide it, but that's gonna take some communication to dial that in. So let's say the fire pump's giving them 100 PSI and for whatever reason they need 120. I would need to increase my engine pressure to 100 before I can give them that extra 20 pounds. Does that make sense? Because I would need a pump 2 and overcome the fire pump. We're gonna do this in November when we do the 8-hour day stuff. We're gonna run a drill that'll help support this. It'll be important to water the stairwell, meaning just like watering the grass, you want to water the stairwell because you're going to want a flowing pressure as you gate back and determine your flow. We're switching the smoothbore tip on our current high-rise pack after this class. The fog nozzle will go into the bag. That can be an important ventilation tool once we get there. It could be one of our only ventilation options on a high-rise. We'll have new hose loads and a new high-rise deployment next year. The high-rise committee is working on all that. They've got a lot of work ahead of them. So here's the chart we have on our pump chart. We see this is right here on the pump chart. Don't exceed 200 PSI, which is the test pressure on standpipes. Charge the standpipe at idle. Pump sprinkler systems at 150. Pretty simple. Equipment proposals. So when we originally gave this presentation to ops, there were a few pieces of equipment that just kind of didn't make sense for us to keep on the engines, but we wanted to present it to everybody at PFA and make sure that we weren't missing something. The first piece of equipment was removing the 2.5-inch Y. That large Y, can't really think of a super safe way to put that into service. I'm not sure what that's doing for us. It takes up room, not sure we need it. We're proposing getting rid of it. If anybody's got any ideas on reasons to keep any of this stuff, please let us know. We're keeping a running tab. We've already heard a few things. We'll bring it to ops and let them make the decision.
Does ISO play into any of these appliances?
No, none of these are on ISO. Yeah, we've looked at that on the equipment committee. The ISO and the NFPA requirements for what's required on an engine are like jokingly minimal. It's hilarious actually when you read it. The 2.5-inch fog nozzle. So at 266 GPM on a smoothbore nozzle, at 50 PSI, we've got 99 pounds of nozzle reaction. That same flow on a fog nozzle gives us 134 pounds of nozzle reaction. Not sure many situations where that's going to come into play. If we're using it defensively, maybe for structure protection, why not just use a blitz fire? Help us manage that nozzle reaction anyway.
It has a great reach, but I mean, your nozzle reaction goes up really quick, and if you pump it hotter than that, it's pretty crazy.
It's really...
It's like 160 pounds of nozzle reaction if you pump it. I think it's up around 325 GPM.
So it's substantial. The rabbit ears, we've already heard a couple arguments towards keeping these. These are the 5-inch storage to the 2 ball valves with the pigtails coming off of it. What these were originally intended for was the hydrants that had the 2.5-inch discharges on it before they had the steamer 5-inch, so you could hook up and lay 5-inch off of that. A 3-inch supply can give you about 1,000 GPM on a good hydrant. 2 3-inch supplies, so if you ran a dual lay, it'd give you about 2,000 GPM. That's a lot of water. I'm not sure there's many situations where we're using these rabbit ears. We've already heard a couple reasons to keep them. We'll definitely bring that to ops. One of the other things with this is we either need to get rid of them or replace them. They're really old. Those ball valves have gotten really loose, and I've seen them on several occasions just slam shut just from water running through it. And we can and have and will break water mains with that. So we either need to replace them or get rid of them. If anyone has any ideas or ways they use those on fires, please let us know. We'll bring that to ops. So we've covered a lot today, right? Let's review what we've covered before we go over pump charts and take our break. May sound like a lot, but when you look at this all in application, it's really not that much. We've increased our flow rate and standardized it from 150 to 180 GPM and low pressure. That gives us a perfectly manageable line for one firefighter. We've talked about mystery hose. The bottom line with that is use the friction loss numbers from the charts. We're not using any more rules of thumb math to determine our friction loss. We've talked about why we use our charts. We'll talk about how in a minute. We talked about how important accuracy is, how 15 PSI makes a huge difference at the end of the nozzle. We've talked about watering the grass, developing that into our culture so we can set an accurate flowing pressure. We've talked about the importance of eliminating kinks, how it's everyone's job on the fire ground. We've talked about Y operations. We're standardizing our Y operations. We talked about Y. Basically, it's a 3-inch supply with 2 3/4 pre-connects of equal length. What do we call it? Supply to a Y. Really, everyone's on the same page. We talked about our hose line selections. We've got 2 offensive lines, 1 3/4 180 GPM, 1 1/8 266 GPM, and 3 offensive options. Our 1 1/4 328, our blitz at 500, and our deck gun aerials and street sets. We talked about high rise, how we're using the pressure gauge and the attack crew on the floor below the fire to determine our line pressure. So we talked about a lot of stuff, but not a ton of real practical changes here. So last thing we're going to talk about before our breakout session is our new pump charts. We just wanted everyone to be on the same page here, including captains, so that when you go to the pump pit, you know what to expect from your DOs. The pump charts are color-coded and split up into 6 different sections. We've got general pumping information, pre-connects, and friction loss. This is 99.99% of everything we're going to use on the chart. Furthermore, everything highlighted in this section is everything you're ever going to need off these charts. The rest of the chart is just a reference if you need it. We have our pump table, big water and high rise, rural operations, and our foam and Bresnan section. So I'm going to write on the wall. I'm going to write up here. If you see me about to write on the wall, please say something because it's happened. So we'll go through the 1 3/4 pre-connect section here, and that's going to tell you how this pump chart works. I'm going to zoom in on this a little bit. So here's our 1 3/4 pre-connect chart. We've got 2 flow rates, 125 GPM for a car fire or a dumpster fire. We have our total line pressure, so that's 1, 2, and 300 foot sections. That incorporates nozzle pressure, friction loss, the whole 9 yards, unless I've got elevation or an appliance for whatever reason. That's my total line pressure. That's all the math done for me. If I need to determine my friction loss and my nozzle pressure, I get that from the chart. I've got a nozzle pressure of 45 and a friction loss of 20 PSI per section. 180 GPM, our new standard for a structure fire. I've got my total line pressures at 1, 2, and 300 feet with 200 feet circled because that's our primary line. I've got my nozzle pressure. Once again, I want to get the nozzle pressure from the charts, that's important. At 125 GPM, my nozzle pressure is 45. At 180 GPM, I'm at 60. That's because of that automatic nozzle. That's why we don't want to just blindly throw numbers at this. Our friction loss is based on flow tests. So let me show you how this works. So if I've got an 1 3/4 pre-connect at 180 GPM, I lose 60 pounds, I need 60 pounds at the nozzle, and I need 35 PSI per section. I've gotten those from my chart. 35, 35. I add that all together and I end up with 130, which is exactly what my chart tells me. If I add another section, I've added another 35 pounds, and my line pressure increases from 130 to 165, which is exactly what my chart tells me.
By section, he means 100 foot.
100 foot, yep. If I have a 50 foot section, I just take half of my friction loss per 100. Does that make sense? So if you know how to use that chart, you know how to use every single chart on this table. So here's our 2.5. I've got 2 different flow rates. I've got my 1 1/8 at 266 GPM and my 1 1/4 at 328 GPM. It works exactly the same. I've got total line pressure from 1, 2, 300 feet. My nozzle pressure, if I have a fog nozzle or a smooth bore, once again, these are based on flow tests, and my friction loss of both those flows. These also have the associated nozzle reaction. Once again, these charts are designed to support our deployment, right? So my other flow rate here, if I'm extending an 1 3/4 at 180 GPM, so well, let me get to that in a minute. First, I'll show you this chart. So if I've got an 1 1/8 tip at 200 feet, sorry, 1 1/8 tip, what's my GPM? 266, it tells me right here. And I've got a nozzle pressure of 50 on a smooth bore, and I'm losing 11 per section for a line pressure of 72, which is exactly what my chart tells me. If I add another section, 100 foot section, I lose another 11 pounds, and I go to 83, which is exactly what my chart tells me. Does that make sense?
Something to keep in mind with the tip sizes too, we've got them highlighted, the ones you're primarily concerned with. You're not having to memorize a whole lot.
Right.
Not only that, but you'll find it to be easier when they are oddball numbers. I mean, most of us probably, you went in order, right? From the one you knew to the one you're at to try and figure out what the GPM on it was, right?
Right.
So you'll actually find out it's a lot easier this way.
Yeah, you'll memorize these GPMs
Super
in no time.
fast.
Because there's really only 3 to memorize. So our only other option was 2.5, because remember, we're not using 2.5 to supply a Y, we're not using it to supply a blitz fire. Our only other option with 2.5 is if we're using it to extend a line, like extend an 1 3/4, right? So let's say I did a big water reset, or I'm extending a line because I don't want to deal with the nozzle reaction of a Y operation. So remember that 2.5 inch bail is 2.5 inch on one side and 1.5 inch on the other. So we can use that as a reducer. So if we pull our 200 foot pre-connect and we take our tip off and we use it as a reducer and we extend it with a 1 3/4 pre-connect to 200 feet, I've got a flow rate for that. If I'm extending an 1 3/4 to 180 GPM with 2.5, I'll allow 5 PSI per 100. All the DOs take special note of where this is at on the chart, because in our breakout session, this is the number one thing this is the only thing on a chart that's in kind of a weird place. But it's in red and it's highlighted. And we have 3 flow rates on our 2.5.
You're extending your 2.5. Just
Right.
remember, like a large water reset, and then you're gonna use it as an attack line to go into the building.
Right. You've got 3 flow rates on a 2.5, 266, 328, and 180. Does that make sense? So if I'm doing that, I get my line pressure that I used before, which is 130 for 180 GPM. I lose 10 for my reducer, which is my nozzle, and I lose 5 PSI per 100 feet, 5, for a total line pressure here of 150 when I add it all together. Does that make sense? So we're just getting the numbers off the charts. This isn't like reinventing the wheel. All we're doing is getting our numbers off the charts.
You'll also start to figure out that those become very common. We don't have lots of variables. That's gonna be the same way you're gonna do that 2.5,
Yep.
1 inch and 3/4 is always gonna be that same way.
By the time you're done with these breakout sessions, you'll have these numbers memorized. They get so quick. So here we've got our high rise. It's no different. We got our flow rate, 200 feet, nozzle pressure and friction loss. I know these numbers are wonky. I'm not going to get into why. Just trust them.
We can if you wanna know later.
Yeah, it's just a lot to get into. Blitz fire is no different. If I've got a 200-foot blitz fire, it's at 500 GPM, always supplied with 3-inch. I get my nozzle pressure. It's just in a different spot on this. Nozzle pressure of 110.
Remember, that includes the friction loss for that blitz fire.
Yep. My friction loss per 100 at 500 GPM is 15, which is 140 total line pressure, which is exactly what the chart tells me. Does that make sense? All the math is done.
Most of the time, you're gonna be able to go right to your pump discharge pressure.
Yep. Gene is here already. So 98% of 99% of everything we're going to use commonly is highlighted. So once again, these charts are designed to support this whole idea of standardized weapons in the box idea. I've got what my lines are and what those lines do. So everything I need is highlighted. All those numbers, these are the big ones. If you can remember these numbers, that's 99% of everything that you need. As far as the rest of the chart, we have general pumping information at the top. That's the blue section here at the top. We've got the pump chart key, which tells us our abbreviations. We've got general friction loss, 5 PSI per story, half PSI per foot, 10 PSI per appliance, 25 for a street set. We've got a quick reference for pump capacity based on discharge pressure and our smoothbore nozzle chart. Our pump table, very little has changed there. We have big water and high rise all in one section. So we've got pump in the towers, starting at 150 PSI to the tailboard and adjust as needed.
And we should have put aerials on there.
Yep, but this is towers. Too late. Deck guns, 5-inch friction loss, additional water from a hydrant, standpipes and sprinkler systems. All in big water and high rise. They're all divvied up into sections so you can find them easy. Rural operations are all put together. Jet siphon, relay, turbo draft, tender capacity. We've got our tender capacity formula to give us our total GPM available at a fire. We've also pre-done some math for you. So if I've got a 15-minute cycle time and 1, 2, or 3 tenders, it tells me my flow rate. So if I've got a 10-minute cycle time and 3 tenders, I can provide 540 GPM. We want to try to get a minimum of 2 inch and 3/4 lines down at a fire. So the black numbers tell me when I'm meeting that need, the brown numbers tell me when I'm not and I need to change something. We've also got some tender setup options here. These are explained in the DO manual as far as setting up your tenders for an efficient operation, and then your final tank configuration on a narrow setup and a wide setup. So we've got our tank sitting in front of the engine or our tank sitting next to the engine. Of course, these aren't going to work in every single situation, but they're going to work in most of them. Last thing on the chart is our foam operations. This is everything we taught in this year's 8-hour day, and the Bresnan nozzle's down here just because it couldn't fit anywhere else and we never really use it, so it's there if you need it. This works exactly the same. You've got your size, your GPM, your flow rate, your friction loss, and your GPM. So our training plan to release this is this class, the 2016 DO manual, which we'll hand out to all the DOs at the end of this class, the November training, which is going to back up the hands-on portion of this, and this is what that drill is going to look like in November. So we're going to have 2 engines, and the goal with this is to get every DO to run through this twice in a row. So you can run through it, and then you can make improvements on it later. So we're going to have this drill and then the exact same drill happening right next door. There's going to be 2 engines. This is really designed to help the DO learn all this stuff and to help us reinforce watering the grass in our high-rise operations. So we're going to, the first engine captain, well, the captains are going to be pulled off and do some stuff for blue card. The first firefighter is going to pull an 1 3/4. The DO is going to perform a hydrant transfer while that line is flowing. Then we're going to pull another 1 3/4 and a 2.5, and then we're going to pick it all up and do it again, and that DO gets the chance to do everything twice. We're going to reinforce nozzle reaction, reinforce watering the grass with all these. While this is all going, Captain Macarini is going to pull DOs off and run them through DO comps, which I'll let him talk about.
Thanks, Mike. So about this time last year when we did the pump theory class, getting everybody all on the same page back on just some fundamental concepts with pumping engines, we mentioned that this year we're going to be doing DO proficiencies. So that, like Mike said, that'll be part of this training as well. We're going to be doing PFA pumping JPR number 1, which is going to be the multi-line pumping JPR. And we're going to focus just on the basic things that is, you working for an officer, they're going to call for quickly. And Mike and Hal are going to be kind of working with you in the breakout session that the DOs will be doing here, running that same type of format that JPR is kind of lined out that way. Everybody was given that as part of your DO packet for this year that you came out and pumped on your own. We supplied a video of me running Hal through that JPR. That was part of that assignment, and it's still on Target Solutions if you need to reference that. And all I'm looking for is that once I give you a line, within that first minute, you need to tell me what that line discharge pressure is, tell me what the GPM of that line is, and then start opening that discharge valve. Okay? Once you do that, then you have the remainder of the 5 minutes to balance everything out. So if that takes you 30 seconds, then you got 4.5 minutes to balance everything out. That's not going to be as critical for that first line you put in service. Everybody should be able to get that first line in service within 30 seconds. It's going to be more critical when you have multiple lines flowing and you're trying to keep everything balanced, so you'll have plenty of time. Review that JPR, review the video of me sending Hal through that, and like I said, you all got practice on that this summer, so that's what we'll be doing. I just finished the training action plan for that. It'll lay out kind of how that'll work. If you're having difficulties that day, you'll be able to retake that JPR that same day. If you have difficulties again, then we'll reschedule it after 30 days, give you some time to kind of practice that. And there's more steps on there, so don't freak out. No one's going to be threatened with their DO status or anything like that. You'd have to go through a lot of steps for that to even be considered at that point. So, and like I said, they're going to run you through all that stuff. They're going to get you very comfortable with that type of format. In addition to that, they're going to be, I think everybody has it, some sample pump problems that I put together for the folks that went through the PFA portion this year. Just kind of give you some ideas of different line orders that you might get. So.
We'll get that out to you with your DO manual.
Okay, I didn't know if those were passed out yet.
We will
Yep.
definitely set you up for success in this breakout session.
Yeah, definitely.
So call me if you have any questions and use those resources that are on Target Solutions to help you get prepped.
Is everybody getting DO manuals or just DOs?
All the stations will get a manual, so we'll send them out, so each station will have a copy, and then all the DOs are getting them too. I promise you, as far as like drawing problems and getting lines into service quickly, you'll leave here comfortable today. All the other crews that have gone through this have feeling very comfortable.
Yeah, we're like halfway through and we had people to the point where they were putting 3 or 4 lines in service in 3 to 4 minutes.
Yep. So real quick, if you're watching at home on the video, this concludes the 2-hour class that everyone's required to go. We're going to break for the breakout session. If you're a DO, stay with us for the next hour, and we're going to do whiteboard problems, and then we might even record yours to get up at some point too, maybe, Gino. I don't know if we will.
Yeah, I'll be sending out stuff.
Okay.
We'll be sending out that same material.
Okay. So if you're watching this at home, we're going to take a quick break. We'll come back and do the DO portion of this, and everybody else take a 10-minute break.